In the summer of 1997, a machine, designed to listen for the end of the world, picked up something it was never meant to hear. Deep beneath the surface of the Pacific Ocean, an array of hydrophones, underwater microphones originally built during the Cold War to track the movements of Soviet nuclear submarines, recorded a sound so powerful, so immense, and so profoundly alien that it sent a quiet ripple of unease through the global scientific community. The sound lasted for roughly 1 minute. It rose in frequency over several seconds, as though something enormous was stirring from a long sleep. And then it stopped. No explanation followed. No repetition came. Just silence, vast and heavy, returning to fill the void where the sound had been. The scientists at the National Oceanic and Atmospheric Administration, who first analyzed the recording, gave it a name that belied its mystery. They called it the Bloop. What made the Bloop extraordinary was not merely its strangeness, it was its sheer, overwhelming power. The sound was detected by sensors positioned more than 5,000 kilometers apart. To translate that into a form the human mind can grasp, imagine standing in the center of New York City and hearing a noise that originated in London, not through a telephone, not through a cable, not through any electronic medium at all, through the raw physical substance of the ocean itself. Whatever made this sound was louder than any known animal on the planet. It was louder than the blue whale, the largest creature known to exist, which produces vocalizations that can reach 188 decibels and be heard across entire ocean basins. The Bloop dwarfed that figure. It dwarfed it not by a small margin, but by a magnitude that left researchers struggling to identify any biological mechanism that could account for it. And the sound originated from one of the most remote, most inaccessible regions of Earth. A point in the southern Pacific Ocean so far from any landmass that the nearest human beings at any given moment are often the astronauts aboard the International Space Station, orbiting more than 400 kilometers overhead. That is not poetic exaggeration. That is a geographical fact. The ocean covers more than 70% of our planet's surface. It holds roughly 1.35 billion cubic kilometers of water. It reaches depths of nearly 11 kilometers in its most extreme trenches, places where the pressure alone would crush a nuclear submarine like an aluminum can beneath the boot heel. And the overwhelming majority of this enormous volume has never been seen by human eyes, not photographed, not filmed, not mapped with any degree of meaningful resolution, not explored by submersible, by robot, or by any instrument of any kind. We have better topographical maps of the surface of Mars than we do of our own ocean floor. We have sent more human beings beyond the atmosphere of this planet than we have sent to the deepest points of the sea that lies beneath our feet. And somewhere within that vast, cold, lightless, unexplored volume of water, something produced a sound that no living creature we know of could have generated. That question, the question of what made the Bloop, is where our journey begins tonight. But the Bloop is only the doorway. Beyond it lies a far larger and more unsettling truth about what the deep ocean contains, what it conceals, and why we may not be prepared for the answers it eventually offers. The deep ocean is not simply dark water. It is a world governed by forces that the human body was never built to endure. Pressure that would collapse a steel chamber. Temperatures that hover just above freezing for thousands of vertical meters. Absolute, total, unbroken darkness that has persisted without a single photon of sunlight for longer than any human civilization has stood. Down in those depths, life does not merely cling to survival. It thrives in forms that bear no resemblance to the life we encounter on the surface. Creatures without eyes, because eyes are useless where no light has ever reached. Creatures that manufacture their own cold, ghostly illumination through chemical reactions in their own tissues. Creatures that feed on toxic chemicals spewing from cracks in the planet's crust at temperatures exceeding 300 degrees Celsius. And yet, despite all of this alien strangeness existing on our own world, we have explored less than 5% of the ocean's total volume. The remaining 95% is as unknown to us as the interior of a world orbiting a distant star. By the end of tonight, you are going to understand why that number, 95%, matters far more than most people have ever been told, and why the Bloop is just one whisper in a chorus of deep ocean mysteries that science has not yet been able to silence. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The story of the Bloop reaches into some of the most fundamental questions human beings have ever asked about their own planet. What lives in the places we cannot reach? What sounds fill the spaces we cannot enter? What truths are concealed beneath the surface we walk beside every single day without giving it a second thought? These are not abstract philosophical puzzles to be debated over coffee. They are active, urgent scientific questions with real implications, and the answers, if and when they arrive, may reshape our understanding of what life is capable of and where it can persist. The ocean is not merely large, it is incomprehensibly large, and in its deepest, darkest, most pressurized corners, it harbors secrets that humanity has only just begun to suspect exist. Tonight, we go looking for them. Now, let us begin. To understand the Bloop and to understand why it matters, we must first understand the arena in which it was heard. The ocean, not the postcard version, not the turquoise shallows where sunlight dances across white sand and children splash in knee-deep water. The real ocean, the deep ocean, the one that begins where the light ends and stretches downward into a blackness so absolute, so total, and so permanent that the human eye becomes functionally useless within minutes of descent. The ocean is the single largest habitat on Earth. It covers approximately 361 million square kilometers of the planet's surface. If you took every continent, every island, every peninsula, every strip of land on the planet and pressed them together into one mass, the ocean would still dwarf them by a wide margin. It holds roughly 97% of all the water on Earth. The volume of water in the ocean is estimated at approximately 1.335 billion cubic kilometers. That number is so large, it resists comprehension, so let us try to approach it from a different angle. If you could somehow drain the ocean and stack its water on top of a single football field, the column of water would extend upward for a distance many times the diameter of the entire planet. The ocean is not simply a body of water sitting on the surface of the Earth. It is the dominant physical feature of this planet. It is the environment in which the majority of life on Earth exists. And it is the environment about which human beings know the least. The average depth of the ocean is approximately 3.7 kilometers. That means that the average point on the ocean floor sits deeper below the surface than most commercial aircraft fly above the ground when at cruising altitude. But that average is deeply misleading because the ocean floor is not a flat, featureless plain. It is a landscape of extraordinary variety and drama, with mountains taller than any on land, canyons deeper than the Grand Canyon, vast flat abyssal plains covered in fine sediment, and narrow, plunging trenches where the seafloor drops to depths that challenge the limits of human engineering and human understanding. In these trenches, the ocean reaches its extremes, and those extremes are where our story eventually leads. The ocean is divided into 5 vertical zones, and understanding these zones is essential to understanding the Bloop and the world from which it emerged. Each zone represents a distinct environment with its own physical characteristics, its own biological communities, and its own relationship to light, pressure, and temperature. The first zone is the epipelagic zone, sometimes called the sunlight zone. It extends from the surface of the ocean down to a depth of roughly 200 meters. This is the ocean that most human beings know. It is the ocean of beaches and boat rides and snorkeling excursions. Sunlight penetrates this layer generously, fueling the photosynthesis of phytoplankton, tiny plant-like organisms that form the base of the marine food chain and produce, by some estimates, more than half of the oxygen in Earth's atmosphere. The water here is relatively warm, ranging from tropical temperatures of over 30 degrees Celsius near the equator to near freezing temperatures in polar regions. The epipelagic zone is home to the vast majority of the ocean's visible life. Fish, dolphins, sea turtles, jellyfish, sharks, rays, whales at the surface, and a teeming microscopic world of plankton and larvae that drifts with the currents. It is a vibrant, light-filled, dynamic environment, and it is a vanishingly thin skin over an abyss. The epipelagic zone, at 200 meters deep, represents less than 3% of the ocean's total depth range. Below it, the world changes. The second zone is the mesopelagic zone, also called the twilight zone. It begins at 200 meters and extends down to roughly 1,000 meters. In this zone, sunlight fades. It does not vanish abruptly, like a light being switched off. It diminishes gradually, passing through shades of deepening blue, then indigo, then a violet so faint it seems more like a memory of color than color itself. By the lower reaches of the mesopelagic zone, the last traces of sunlight have been absorbed by the water above, and the darkness becomes total. The temperature drops significantly in this zone, often falling to between 5 and 10 degrees Celsius, and the pressure increases relentlessly. Every 10 meters of descent through seawater adds approximately 1 atmosphere of pressure to whatever is descending. At the surface, the pressure is 1 atmosphere, the standard air pressure at sea level. At 100 meters, it is 11 atmospheres. At 500 meters, it is 51 atmospheres. At 1,000 meters, the bottom of the mesopelagic zone, it is 101 atmospheres. That means every square centimeter of surface at that depth bears a force equivalent to roughly 101 kilograms. That is the weight of a full-grown adult pressing on an area smaller than a postage stamp. The creatures that live in the mesopelagic zone have adapted to these conditions in remarkable ways. Many of them are bioluminescent, meaning they produce their own light through chemical reactions within their bodies. In a world without sunlight, the ability to generate light is a survival tool of extraordinary importance. Some creatures use bioluminescence to attract prey, dangling a glowing lure in front of cavernous jaws. Others use it to communicate with potential mates across the lightless water. Still others use it defensively, producing sudden flashes of light to startle predators or releasing glowing fluids to confuse pursuers. The mesopelagic zone is one of the most densely populated layers of the ocean by biomass, despite its apparent inhospitability. Vast populations of small fish, shrimp, squid and jellyfish make their home here, and many of them undertake a daily vertical migration that is considered the largest animal migration on Earth. Each evening as the sun sets and the surface darkens, billions upon billions of these creatures rise from the mesopelagic zone into the epipelagic zone to feed under cover of darkness. Each morning as the sun rises, they descend again into the twilight to avoid visual predators. This migration, repeated every single day, involves more biomass than any other animal movement on the planet, and it was not discovered until the mid-20th century, when sonar operators aboard naval vessels noticed a mysterious deep scattering layer that rose and fell with the cycle of day and night. Below 1,000 meters, the third zone begins. This is the bathypelagic zone, also known as the midnight zone, and here the word darkness takes on its full and terrible meaning. There is no sunlight at this depth, not a glimmer, not a trace, not the faintest ghost of illumination from the surface above. A human being placed in the midnight zone without artificial light would see absolutely nothing. Not the outline of their own hand, not the faintest suggestion of shape or movement. The darkness is total, permanent, and complete. It has been this way for as long as the ocean has existed in its current form, and it will remain this way regardless of what happens on the surface. The temperature in the bathypelagic zone is cold, between 0 and 4 degrees Celsius in most regions. The pressure is crushing. At 2,000 meters, approximately 201 atmospheres. At 3,000 meters, approximately 301 atmospheres. At 4,000 meters, the lower boundary of this zone, approximately 401 atmospheres. To visualize this pressure, imagine stacking roughly 400 standard automobiles, each weighing approximately 1,500 kilograms, on top of a platform 1 meter square. That is the force the water exerts at the bottom of the midnight zone, on every square meter, at every moment, without pause, without variation, without mercy. The life that exists in the bathypelagic zone is sparse compared to the zones above, but it is not absent. The creatures here tend to be specialized and strange. The anglerfish, with its bioluminescent lure dangling from a modified dorsal spine above a mouth filled with needle-like teeth, is perhaps the most iconic resident. The giant squid, which can reach lengths of 13 meters or more, hunts in these waters. The gulper eel, with a jaw that can unhinge to engulf prey larger than itself, drifts through the blackness. The black swallower, a fish barely 25 centimeters long, can consume prey more than 10 times its own mass by distending its stomach to accommodate the meal. These creatures live in a world where food is scarce and encounters between predator and prey are rare and unpredictable. Every meal matters. Every encounter is potentially the last. The adaptations that have developed here are not elegant. They are desperate, efficient, and often grotesque by the standards of surface life. Below 4,000 meters, the fourth zone begins. This is the abyssopelagic zone, a name derived from the Greek word abyssos, which means bottomless or without depth. For most of human history, people believed the ocean truly had no bottom in these regions. The idea that the ocean floor existed as a tangible surface at such extreme depths was not confirmed until the development of echo-sounding technology in the early 20th century. The abyssopelagic zone extends from roughly 4,000 meters to 6,000 meters. The temperature is near freezing, typically between 1 and 4 degrees Celsius. The pressure exceeds 400 atmospheres and approaches 600 atmospheres at the zone's lower boundary. The landscape here is dominated by vast abyssal plains, some of the flattest surfaces on Earth, covered in a fine layer of sediment composed of the accumulated remains of dead organisms that have drifted down from the waters above over millions of years. This sediment, often called marine snow, is the primary food source for abyssal communities. It consists of tiny fragments of dead plankton, fecal pellets, discarded mucus structures, and other organic debris. It falls through the water column with agonizing slowness, taking weeks or even months to travel from the surface to the abyssal floor. By the time it arrives, most of its nutritional value has been consumed or degraded by organisms in the zones above. What reaches the bottom is a thin, pale, nutrient-poor rain that sustains an ecosystem operating on the barest margins of survival. The organisms that live on the abyssal plains are small, slow-moving, and metabolically efficient. They cannot afford to waste energy. Sea cucumbers creep across the sediment, filtering it for organic particles. Tiny amphipods scavenge whatever larger pieces of food happen to reach the bottom. Bacteria colonize every available surface, extracting energy from the chemical compounds in the sediment. Life persists here, but it operates at a pace and a scale that would be unrecognizable to a surface dweller. The abyssopelagic zone also contains some of the most dramatic geological features on Earth. Seamounts, underwater mountains formed by volcanic activity, rise from the abyssal beach to heights of 1,000, 2,000, sometimes 3,000 meters or more, without ever breaking the ocean surface. Some of these seamounts are taller than any mountain in the Alps or the Rockies, and they harbor their own distinct ecosystems, communities of corals, sponges, and fish that cluster on their slopes to take advantage of the nutrient-rich currents that flow around them. The total number of seamounts in the world's oceans is estimated at over 100,000, and the vast majority have never been surveyed in any detail. Each one is potentially a unique habitat. Each one potentially harbors species found nowhere else on Earth, and almost none of them have been visited by a human being or a human-operated vehicle. Below 6,000 meters lies the fifth and final zone, the Hadal Zone. It is named after Hades, the ancient Greek realm of the dead, and the name is fitting. This is the domain of the ocean trenches, the deepest scars on the face of the Earth, carved by the collision and subduction of tectonic plates. There are approximately 33 Hadal trenches in the world's oceans, and together they represent the most extreme environment on the planet's surface. The deepest of these is the Mariana Trench, located in the western Pacific Ocean east of the Mariana Islands. Within the Mariana Trench lies Challenger Deep, the deepest known point on the surface of the Earth. The depth of Challenger Deep has been measured at approximately 10,935 meters below sea level. To grasp this number, consider a comparison. Mount Everest, the tallest mountain on Earth, rises to a height of 8,849 meters above sea level. If you could take Mount Everest, entire and intact, and place it at the bottom of the Mariana Trench, with its base resting on the floor of Challenger Deep, the summit of the mountain would still be submerged beneath more than 2,000 meters of ocean water. More than 2 full kilometers of water would sit above the peak of the tallest mountain on the planet. That is not a scaled model or an artistic representation. That is the actual dimensional comparison between the deepest point in the ocean and the highest point on land. The ocean is deeper than the land is tall, and it is deeper by a significant margin. Another way to grasp the depth of Challenger Deep is to consider time. If you were to drop a steel ball bearing from a ship directly above Challenger Deep, that ball bearing would take more than 1 hour to reach the bottom, sinking through zone after zone, passing through light, and then twilight, and then permanent midnight, the pressure building around it with every meter of descent. 1 hour of falling through water, straight down, before reaching the floor. And during that hour of descent, the ball bearing would pass through environments that contain creatures, geological features, and chemical conditions that we have never documented. The descent itself would be a journey through the unknown. The pressure at the bottom of Challenger Deep is approximately 1,086 atmospheres. One way to conceptualize this is to imagine taking a standard sedan, a car that weighs roughly 1,500 kilograms, and stacking more than 1,000 of them on top of a platform measuring 1 meter by 1 meter. The weight of that stack, pressing downward on small area, would approximate the force that the ocean exerts on every square meter of surface at the bottom of the trench. Another way to think about it is this. At the surface of the ocean, the air pressure we breathe and move through without noticing is 1 atmosphere. At the bottom of Challenger Deep, the pressure is more than 1,000 times greater. A human lung, which inflates against 1 atmosphere without effort, would be compressed to a volume smaller than a marble. The human body, which is roughly 60% water and therefore somewhat resistant to compression, would nonetheless suffer catastrophic failure long before reaching such depths without protection. The first manned descent to Challenger Deep took place on January 23, 1960. Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh climbed into the bathyscaphe Trieste, a deep-diving vessel designed to withstand the full pressure of the Hadal zone, and began their descent into the darkness. The dive took nearly 5 hours. When they reached the bottom, at a depth of approximately 10,916 meters, they peered through the small porthole of the Trieste and saw something unexpected. A flatfish lying on the sediment, apparently alive and healthy at the deepest point on Earth. The sighting was later disputed. Some researchers suggested it may have been a sea cucumber rather than a fish, but the symbolic importance was undeniable. Life existed at the very bottom of the world. No human returned to that depth for more than 50 years. In 2012, filmmaker James Cameron made a solo descent in the Deep-Sea Challenger submersible, reaching a depth of approximately 10,008 meters. Cameron spent roughly 3 hours at the bottom, collecting samples and filming the barren, pale sediment of the trench floor. He described the experience as desolate, lunar, and profoundly isolated. In 2019, explorer Victor Vescovo piloted the submersible limiting factor to the bottom of Challenger Deep, reaching a depth that slightly exceeded Cameron's. Vescovo subsequently made multiple additional dives, becoming the first person to reach the deepest point in every ocean on Earth. And on one of those dives, at the bottom of the Mariana Trench, he found something disturbing: a plastic bag and candy wrappers, human refuse, carried by currents and gravity to the most remote point on the planet's surface. Even the places we have never been are not untouched by our presence. The Hadal Zone is also home to some of the most extreme biological discoveries of recent decades. In 2005, a Japanese research team filmed a living giant amphipod at a depth of nearly 8,000 meters in the Japan Trench. The creature, a supergiant amphipod, measured roughly 34 centimeters in length, enormous for a species that on the surface would typically measure only a few centimeters. The phenomenon, known as deep-sea gigantism, is observed in several Hadal species and is thought to be related to the slower metabolic rates and reduced competition at extreme depths. Other Hadal creatures have revealed biochemical adaptations that challenge our understanding of the limits of biology. Snailfish found in the Mariana Trench at depths exceeding 8,000 meters have been shown to produce a molecule called trimethylamine N-oxide, or TMAO, in extraordinarily high concentrations. This molecule stabilizes their proteins against the crushing pressure that would otherwise cause them to malfunction and collapse. Without TMAO, no vertebrate could survive at such depths. With it, a small, pale, seemingly fragile fish can swim through pressures that would destroy a nuclear submarine. These discoveries are relevant to the Bloop because they illustrate a crucial point about the deep ocean. It is not empty. It is not lifeless. It is not a barren wasteland of water and rock. It is an active, populated environment where organisms have developed capabilities that surface biology cannot easily explain or predict. And if the deep ocean can produce creatures with antifreeze in their blood and pressure-resistant proteins in their cells, the question of what else it might contain is not a question of fantasy. It is a question of inventory. We simply have not finished counting. We have barely begun. And it was into this layered, pressurized, lightless, biologically strange world that the Bloop travelled. A rising note of unknown origin, threading its way through the deep sound channel, crossing thousands of kilometers of ocean in the space of minutes, and arriving at a chain of Cold War hydrophones that happened to be listening at exactly the right moment. The ocean speaks constantly. We heard one word, and we did not understand it. The question, once asked, could not be unasked, and the scientist who heard it would spend years searching for an answer that the ocean seemed unwilling to give. It was into this layered, pressurized, lightless world that the sound of the Bloop travelled in the summer of 1997. The system that detected it was not designed to search for ocean mysteries. It was designed to hunt submarines. During the Cold War, the United States Navy deployed a vast network of underwater listening stations known as the Sound Surveillance System, or SOSUS. These hydrophones were placed at strategic depths and locations throughout the Atlantic and Pacific Oceans, positioned to exploit a remarkable physical phenomenon called the Deep Sound Channel, also known as the SOFAR Channel. The Deep Sound Channel exists at a depth of roughly 700 to 1,000 meters in most ocean basins, though its exact depth varies with local conditions. At this depth, a combination of temperature and pressure creates a zone where the speed of sound reaches its minimum value. Sound waves that enter this channel are refracted inward, bent back toward the channel axis, rather than dispersing outward in all directions. The result is a natural acoustic waveguide, a corridor through which sound waves can travel extraordinary distances with minimal loss of energy. A sound generated in the SOFAR channel off the coast of one continent can be detected off the coast of another, thousands of kilometers away. The ocean, it turns out, is not the silent world that early explorers imagined. It is a world saturated with sound. Whale songs crossing entire ocean basins, the deep rumble of undersea earthquakes, the sharp crack of volcanic eruptions on the mid-ocean ridges, the constant, soft hiss of rain falling on the surface, the clicking of snapping shrimp colonies, so intense they can interfere with military sonar operations, and occasionally, something that defies classification. After the Cold War ended, portions of the SOSUS network were declassified and made available to civilian scientists. NOAA began using the hydrophones to monitor natural oceanic phenomena, seismic activity, whale migration patterns, ice dynamics, and the general acoustic environment of the deep ocean. It was in this capacity, during the summer of 1997, that NOAA's Pacific Marine Environmental Laboratory detected a series of unusual, ultra-low frequency sounds emanating from the remote southern Pacific. Among these sounds was the one that would come to be known as the Bloop. The recording, when sped up to 16 times its original speed to bring it into the range of human hearing, has a quality that is difficult to describe and impossible to forget. It rises, it swells. It sounds to many listeners unmistakably alive, like the call of something breathing in the darkness. When scientists first analyzed the Bloop's waveform, they noted something that drew immediate attention. The sound's spectral profile, the pattern of its frequencies over time, was consistent with a biological origin. It had characteristics that were more typical of sounds produced by living organisms than of sounds produced by geological processes such as earthquakes or volcanic eruptions. The frequency was low, concentrated below 100 Hz, in the infrasonic range below normal human hearing. And its amplitude, the raw power of the sound, was beyond anything any known animal could produce. The blue whale, the largest creature on Earth, with a body exceeding 30 meters in length and a mass exceeding 170 tons, produces calls that reach 188 decibels. The bloop was detected at distances, suggesting an energy output far exceeding any blue whale vocalization ever recorded. If a living creature made the bloop, that creature would need to be many times the size of a blue whale. No such creature has ever been documented. No bones, no tissue, no carcass, no photograph. The question hung in the air, heavy as the pressure at the bottom of the Mariana Trench. To fully appreciate the weight of this question, it is necessary to understand just how thoroughly the SOSUS system was covering the ocean at the time. The network consisted of arrays of hydrophones mounted on the ocean floor, connected by cables to shore-based processing stations. During the Cold War, the system tracked Soviet submarine movements with remarkable precision, able to detect the faint acoustic signatures of submarine engines and propellers across thousands of kilometers. When this technology was handed to ocean scientists in the early 1990s, it opened a window into the acoustic life of the deep ocean that had never existed before. For the first time, researchers could listen to the ocean continuously, across vast areas, and with sensitivity far exceeding any civilian equipment previously available. The NOAA team that monitored the Pacific hydrophone arrays in 1997 was led by Christopher Fox, an acoustic scientist who had been studying ocean sounds for years. Fox and his colleagues had already catalogued dozens of recurring sound types: the low moans of fin whales, the sharp cracks of underwater earthquakes, the slow rumble of ice movement in the Southern Ocean. They had developed a library of known sounds against which new recordings could be compared. When the bloop appeared on their spectrograms, it did not match anything in the library. It was something new, something unclassified, and in a field where most sounds can be identified within minutes by comparing their spectral signatures to known sources, an unclassified sound of this magnitude was an event of genuine scientific significance. The sound was detected by multiple hydrophone stations, separated by enormous distances. The precise coordinates of its origin were calculated through a process called triangulation, in which the differences in arrival times at different stations are used to determine the location of the source. The bloop was traced to a point at approximately 50 degrees south latitude and 100 degrees longitude, deep in the southern Pacific Ocean. This area is one of the most remote locations on the surface of the Earth. It falls within a region sometimes called the oceanic pole of inaccessibility, the point in the ocean that is farthest from any landmass in every direction. The nearest significant land is Easter Island, roughly 2,500 kilometers to the north. The nearest continental coast is southern Chile, over 3,000 kilometers to the east. Antarctica lies roughly 1,500 kilometers to the south. There are no shipping lanes, no fishing fleets, no coastal communities, no permanent human presence of any kind. It is, by any definition, one of the loneliest places on Earth. The remoteness of the bloop's origin raises an important point about the nature of ocean exploration. Even with modern satellite technology, even with GPS and global shipping networks and the internet, there are vast areas of the ocean where no human eye has looked and no human instrument has listened. The SOSUS hydrophone arrays covered specific corridors that were strategically important during the Cold War. They did not cover the entire ocean. The Southern Pacific, in particular, was poorly monitored because it held less strategic value during the submarine conflicts of the Cold War era. The fact that the bloop was detected at all was in some ways fortunate. Had the sound occurred a few hundred kilometers outside the range of the nearest hydrophone array, it would have gone unheard and unknown, one more piece of data lost to the silence of the deep. This brings us to a critical question that underlies the entire investigation. For every bloop that was detected, how many similar sounds were produced in regions where no instruments were listening? The answer, almost certainly, is that we do not know. We cannot know. The ocean is too vast, and our listening capacity is too limited. The SOSUS network, even at its Cold War peak, covered only a small fraction of the total ocean volume. Modern hydrophone deployments have expanded our coverage somewhat, but the fundamental problem remains. We are listening to the ocean through a handful of keyholes and drawing conclusions about the entire house. The sounds we have catalogued are not a representative sample of the sounds the ocean produces. They are a biased sample, drawn from the specific locations where we happen to have placed our instruments. With this foundation established, the scale of the ocean, the layered structure of its depths, the physics of underwater sound, and the limitations of our listening capacity, the mystery of the bloop begins to take on its full dimensions. This was not simply a strange noise picked up by a microphone. This was a profoundly powerful signal emerging from one of the most remote and least understood environments on the planet, detected by instruments that were listening to only a fraction of the ocean's total acoustic output, and bearing a spectral signature that did not match any known source, biological, geological, or human-made. What made the bloop? But what scientists discovered next was worse than anyone expected. The bloop was not alone. That is perhaps the most important fact that popular accounts of the story tend to leave out. The bloop was not a single isolated anomaly in an otherwise well-understood acoustic landscape. It was one of several unidentified sounds detected by NOAA's hydrophone network during the late 1990s, a period that might be described as the golden age of mysterious ocean recordings. And the collective story of these sounds paints a picture that is far more unsettling than any single anomalous event. In 1997, the same year the bloop was recorded, NOAA detected another mysterious signal they called slowdown. This was a gradually decreasing frequency sound that lasted for approximately 7 minutes. Unlike the bloop's brief, rising note, slowdown was a long, descending groan, as though something massive was winding down, decelerating, coming to a stop after sustained effort. It was detected across the entire Pacific Ocean basin, meaning it carried extraordinary energy. Initial analysis could not match it to any known source. A few years earlier, in 1991, a sound called upsweep had been recorded, a narrow band, recurring signal with a rising tone that appeared with enough regularity to suggest it was not a random event. Upsweep was traced to a general area in the eastern Pacific, near a chain of underwater volcanoes, but its precise source was never positively identified. Then came Julia, detected in March of 1999, a sound lasting approximately 15 seconds that was picked up by the Equatorial Pacific Ocean Autonomous Hydrophone Array. Julia's spectrogram showed a complex, multi-layered structure that some listeners described as a moan or a cry. And there was train, a steady, low-frequency signal that sounded eerily like the distant rumble of a locomotive crossing a bridge, detected intermittently for extended periods, without a confirmed explanation. Each of these sounds shared certain fundamental qualities. They were all extraordinarily powerful, detected across oceanic distances by instruments designed to hear nuclear submarines. They were all in the low-frequency range, below the threshold of human hearing in their original form. They all occurred in remote areas of the Pacific or Southern Oceans, and they were all, at the time of their detection, unidentified, meaning they did not match the spectral signatures of any known biological, geological, or anthropogenic source in NOAA's existing catalogue of ocean sounds. To appreciate the significance of this cluster of mysterious sounds, it is important to understand how comprehensive that catalogue was and how it was assembled. Since the early 1990s, NOAA had been systematically building a reference library of ocean sounds. Every time a sound was detected by the hydrophone network, it was recorded, analysed, and compared to the existing library. If it matched a known source, a blue whale call, a seismic event, a passing ship, it was classified and filed. If it did not match anything in the library, it was flagged for further investigation. Over the years, the library grew to include hundreds of distinct sound types, the songs of dozens of whale and dolphin species, the acoustic signatures of earthquakes at various magnitudes and distances, the noise profiles of different classes of ships, the sounds of underwater volcanic eruptions, the creaking and groaning of ice, the snapping of pistol shrimp colonies, and many more. The catalogue was, by the standards of the late 1990s, remarkably comprehensive, and yet the bloop and its companion sounds did not fit. This failure to classify was not the result of sloppy analysis or incomplete comparison. It was the result of the sounds genuinely not matching anything previously observed. The researchers who analysed them had access to decades of accumulated acoustic data and the expertise to interpret it. They knew what whales sounded like. They knew what earthquakes sounded like. They knew what ice sounded like, or at least they knew what ice had sounded like in the recordings available to them at that time. The bloop was different, not dramatically different, not different in a way that immediately suggested an alien or supernatural origin, but different enough in specific and measurable ways to resist comfortable classification. The question of biological origin deserves particular attention because it is the hypothesis that most captured the public imagination, and the one that continues to intrigue even after the icequake explanation was proposed. The deep ocean is home to creatures that stretch the boundaries of what biology can accomplish. Consider the colossal squid, Mesonatututhis hamiltoni, which inhabits the deep waters of the Southern Ocean, the same general region where the bloop was detected. The colossal squid is estimated to reach lengths of up to 14 meters and masses of up to 750 kilograms, making it the heaviest known invertebrate on Earth. Unlike its cousin, the giant squid, which has suckers lined with small teeth, the colossal squid has suckers equipped with sharp swiveling hooks that can grip prey with extraordinary force. The species was first described from fragmentary remains in 1925, but a complete specimen was not obtained until 2003, when a fishing vessel operating in the Ross Sea hauled up a nearly intact individual. To this day, no colossal squid has ever been filmed alive in its natural habitat. We know it exists, we have physical specimens, but we have never seen it swimming free in the deep water it calls home. If an animal as large and as formidable as the colossal squid can evade direct observation for decades in the modern ocean, the question of what else might be down there is not merely theoretical, it is empirical. The deep ocean provides concealment on a scale that no terrestrial environment can match. An animal living at depths of 2,000 to 4,000 meters in the open Southern Ocean would be surrounded by darkness, cold, and pressure that makes observation extraordinarily difficult. It would be far from any shipping lanes or fishing grounds that might produce accidental encounters. And it would exist in a region of the ocean that has been visited by scientific expeditions a handful of times at most. The probability of encountering such an animal by chance is not zero, but it is vanishingly small. The blue whale, despite being the largest animal on the planet, was itself poorly understood until relatively recently. Blue whale population numbers were not accurately estimated until satellite tracking and acoustic monitoring techniques were developed in the late 20th century. Before that, our knowledge of blue whale distribution, behavior, and population size was based largely on whaling records and occasional sightings from research vessels. The ocean's capacity to conceal even the largest organisms is well documented. The question is not whether the ocean could hide a large animal. The question is whether there is positive evidence that such an animal exists. And for the bloop, the answer to that question remains uncertain. The bloop, however, captured the public imagination in a way none of the others did. Part of this was its name, which had a playful, almost comical quality that made it easy to remember and share. Part of it was the spectrogram image, which showed a distinctive rising curve that looked like a signature scrawled in frequency and time. An elegant, almost artistic shape that was easy to display in a news article or on a website. But the primary reason the bloop became famous was the early assessment by NOAA scientists that its spectral profile was consistent with a biological source. The word biological was the match that lit the fire. If the sound was biological, it was produced by a living organism. If it was produced by a living organism, that organism was of a size beyond anything currently known. And if such an organism existed in the deep ocean without ever having been seen, then the ocean was harboring a secret of staggering proportions. Christopher Fox, The NOAA acoustician who oversaw the analysis was careful in his public statements. He noted that the Bloop's profile was consistent with a biological origin, but he did not claim that it was definitively biological. In science, consistency is a weaker claim than confirmation. A sound can be consistent with a biological source, while also being consistent with non-biological sources that happen to produce similar spectral patterns. Fox was attempting to describe the data honestly, to say what the data suggested, without overstepping the boundaries of what could be proven. But the nuance was lost in the wave of media coverage that followed. Headlines declared the ocean had produced a sound too loud for any known animal. Articles speculated about undiscovered giant creatures lurking in the deep. The internet, still in its early growth phase in the late 1990s and early 2000s, amplified the story into a global phenomenon. The Bloop became a cultural artifact as much as a scientific one. The coordinates where the Bloop originated added another dimension to the mystery. The sound was triangulated to a region near 50 degrees south latitude and 100 degrees west longitude. Those with a taste for literary coincidence pointed out that these coordinates are remarkably close to the fictional location given by the writer H.P. Lovecraft for the sunken city of R'lyeh, the supposed resting place of the cosmic entity Cthulhu. In his 1928 story, The Call of Cthulhu, Lovecraft placed R'lyeh at 47 degrees 9 minutes south latitude, 126 degrees 43 minutes west longitude. The proximity between the Bloop's estimated origin and Lovecraft's fictional city, while clearly a coincidence, was too striking to ignore. Lovecraft had chosen his coordinates to represent maximum oceanic isolation. The Bloop emerged from nearly the same patch of maximally isolated ocean. The coincidence meant nothing in scientific terms, but in psychological terms, it was gasoline on an already burning fire of speculation. The scientific investigation that followed the Bloop's detection was methodical and serious, as it should have been. NOAA researchers, working with acousticians from the Scripps Institution of Oceanography, the Woods Hole Oceanographic Institution, and other centers of expertise, subjected the Bloop's waveform to detailed analysis. They compared its spectral characteristics to the known signatures of blue whale vocalizations, fin whale calls, humpback songs, and the calls of other large marine mammals. They compared it to the known acoustic profiles of underwater earthquakes, volcanic eruptions, and submarine landslides. They compared it to the sounds produced by ships, military sonar, and underwater construction activities, and they compared it to a growing database of sounds attributed to ice dynamics in the Southern Ocean. The results of these comparisons were inconclusive. The Bloop shared some characteristics with blue whale calls: the low frequency, the gradual modulation, the general shape of the spectrogram. But it differed in key respects. Its amplitude was far greater, its duration was longer than most individual whale calls, and its frequency profile, while resembling a biological call in its overall contour, did not precisely match any specific species. The Bloop also shared some characteristics with known geological sounds, particularly the low-frequency rumbles associated with submarine volcanic activity. But geological events typically have sharper onsets and different frequency distributions. The Bloop's gradual rise was not typical of earthquakes or eruptions, and the Bloop did not match any anthropogenic source. Its location, deep in the uninhabited southern Pacific, was not near any shipping lanes, military testing zones, or industrial activities that could have produced such a signal. For several years, the Bloop sat in a scientific limbo. It was too unusual to be confidently classified, too powerful to be dismissed, too singular to allow for repetitive testing. A sound that occurred once, in a remote location, and was never heard again is one of the most frustrating objects a scientist can encounter. Science depends on replication. It depends on the ability to observe a phenomenon multiple times, under controlled, or at least comparable conditions, and to test hypotheses against repeated data. The Bloop offered none of this. It was a single data point, unrepeated and unrepeatable, and the only instruments that had recorded it were listening from hundreds or thousands of kilometers away. In the years that followed the Bloop's detection, a slow but steady accumulation of research on ice acoustics in the Southern Ocean began to reshape the conversation. Scientists studying the Antarctic ice sheet and the massive icebergs that calve from its edges had begun deploying their own hydrophone arrays to monitor the acoustic signatures of ice dynamics. They discovered that the process of ice calving, the fracturing, breaking, and separation of large masses of ice from glaciers and ice shelves, produces an extraordinarily diverse range of sounds. Some calving events produce sharp cracks, others produce prolonged groans, some produce sounds that sweep upward in frequency, from low to high, over periods of seconds to minutes. The variety was far greater than anyone had previously appreciated. This discovery was significant because it expanded the range of known natural sounds that could potentially explain unidentified recordings like the bloop. If ice calving could produce a sound that swept upward in frequency over a period of roughly 1 minute, then the bloop's distinctive rising note might not require a biological explanation at all. In 2005, NOAA released a statement indicating that the bloop's acoustic signature was consistent with large-scale ice calving events, specifically icequakes, the fracturing of large ice masses that generates powerful, low-frequent sound waves that propagate through the deep sound channel. The statement was reported widely as the solution to the bloop mystery. The headlines declared it solved. The monster was ice. But here is what makes this truly terrifying. The explanation, while plausible and widely accepted, was not a definitive identification. It was a best fit match within the available data, and the available data had significant gaps. The ice calving hypothesis rested on a comparison between the bloop's spectral profile and the general characteristics of icequake recordings. But no specific calving event was identified as the source of the bloop. No particular glacier or ice shelf was linked to the sound. No satellite observation of a calving event at the right time, and the right location was cited as corroborating evidence. The hypothesis was that the bloop sounded like an icequake, and that icequakes were known to occur in the general region where the bloop was detected. This is reasonable inference. It is a defensible scientific position, but it is not the same as a confirmed explanation. The difference between consistent with and caused by is the difference between a hypothesis and a conclusion, and in the case of the bloop, we have the former but not the latter. It is also worth noting what was not done in the wake of the bloop's detection. No dedicated expedition was sent to the coordinates where the sound originated. No instruments were deployed in the specific area to monitor for a recurrence. No systematic survey of the local seafloor was conducted to identify potential geological or biological sources. The reasons for this were practical rather than scientific. The location was extraordinarily remote, thousands of kilometers from the nearest port. The cost of an expedition to the area would have been substantial, and the probability of detecting a recurrence of a single, brief, unrepeated sound was considered too low to justify the expense. These practical constraints are understandable, but they mean that the investigation of the bloop was conducted entirely through analysis of existing recordings, rather than through direct observation of the source area. The bloop was studied the way a detective might study a crime scene photograph, carefully, analytically, but without ever actually visiting the scene. Several aspects of the bloop continued to trouble researchers even after the icequake hypothesis became the mainstream explanation. The bloop's frequency contour, that smooth, gradual, upward sweep, was unusually clean and uniform for an icequake. Most icequake recordings show more irregular, chaotic patterns, reflecting the complex and unpredictable nature of ice fracturing. The bloop signal was almost too coherent, too structured, too suggestive of a single, unified source, rather than the distributed, chaotic cracking of a large ice mass. Some researchers noted this discrepancy in their analyses. Others dismissed it as within the normal range of variation for ice sounds. The debate, quiet and confined to academic circles, never fully resolved. There was also the question of timing. The bloop was detected multiple times over the summer of 1997. This pattern, repeated occurrences over a limited period, followed by permanent silence, is more consistent with a biological source, an animal vocalizing during a particular season before migrating or dying, than with ice calving, which tends to occur sporadically and unpredictably throughout the year. The seasonal pattern does not rule out ice. It is possible that a particular ice mass underwent a series of fracturing events during the summer months and then broke apart completely, ending the sound. But the pattern is noteworthy, and it adds a small but meaningful piece of ambiguity to the icequake explanation. And it gets worse. The broader context of deep ocean acoustics reveals that the bloop is not the only sound for which the "it was probably ice" explanation has been invoked and subsequently questioned. Multiple unidentified sounds from the NOAA catalogue have been tentatively attributed to ice dynamics in the Southern Ocean. In some cases, this attribution is well supported by corroborating data. In other cases, it functions more as a default explanation, a scientifically respectable way of saying we do not know, but ice is the most likely candidate based on what we currently understand. The danger of default explanations is that they can become self-reinforcing. Once a plausible explanation has been proposed and widely accepted, the motivation to investigate further diminishes. Funding agencies are less likely to support research into a solved mystery. Researchers are less likely to publish papers challenging a consensus. And the public, satisfied that the question has been answered, moves on to the next curiosity. The result is that genuinely unresolved mysteries can be effectively closed by an explanation that is probable but not proven. To understand the physics of why the bloop was so difficult to classify, it helps to consider the nature of underwater sound in more detail. Sound in the ocean is not a simple phenomenon. It is affected by temperature, by salinity, by pressure, by the presence of boundaries such as the ocean surface and the ocean floor, by the shape of the seafloor, by the presence of underwater structures such as seamounts and ridges, and by the movement of water masses with different thermal and chemical properties. A sound produced at one point in the ocean will be refracted, reflected, absorbed, and scattered by all of these factors as it propagates outward. By the time the sound reaches a hydrophone hundreds or thousands of kilometers away, its waveform may have been significantly altered from its original shape. This means that the sound recorded by a distant hydrophone is not an exact replica of the sound at its source. It is a modified version, shaped by the medium through which it traveled. Two very different sources could, in principle, produce very similar sounds at a distant receiver if the propagation paths and environmental conditions happen to modify the signals in complementary ways. This propagation problem is one of the fundamental challenges of ocean acoustics. It means that identifying the source of a remote sound is always, to some degree, an exercise in inference rather than observation. You hear the sound as it arrives at your location, and you work backward, using models of the ocean environment and knowledge of known sources to estimate what the sound might have been like at its origin and what might have produced it. This process is imperfect. It depends on the accuracy of the environmental models, which are themselves based on incomplete data about the ocean's physical properties. And it depends on the completeness of the catalogue of known sources, which is also incomplete. The identification of the bloop as an icequake is the product of this inferential process, and it carries all of the uncertainties inherent in that process. None of this means the icequake explanation is wrong. It may well be correct. The balance of evidence, as currently understood, favours it, but the certainty with which it is often presented, the bloop was ice, case closed, does not accurately reflect the degree of confidence that the evidence supports. A more honest statement would be, the bloop was most likely caused by an icequake. Based on a comparison of its spectral characteristics with known icequake recordings, but the specific source event has not been identified, and some aspects of the bloop's acoustic profile remain imperfectly explained. That statement is less satisfying. It is less shareable. It does not make for a good headline, but it is closer to the truth. And in science, proximity to truth is supposed to be the goal. The bloop also raised a deeper question about the way we classify unknown phenomena. When confronted with something we do not understand, there is a powerful human tendency to reach for the nearest available explanation, even if that explanation is incomplete. This tendency is not laziness, it is efficiency. In a world of limited time and resources, it makes sense to accept the most plausible explanation and move on, reserving skepticism for cases where the evidence clearly warrants it. But the deep ocean is a domain where our baseline of knowledge is so limited that the most plausible explanation may not be the correct one. Consider the history of ocean exploration and how consistently it has overturned established assumptions. In the mid-19th century, the leading scientific theory held that life could not exist below approximately 550 meters in the ocean. This hypothesis, championed by the British naturalist Edward Forbes after his dredging surveys of the Aegean Sea in the 1840s, proposed that the deep ocean was an azoic zone, a lifeless desert of cold, dark, pressurized water where no organism could survive. Forbes was a respected scientist, and his hypothesis was based on the best available data. His dredges had recovered fewer and fewer organisms with increasing depth, and he extrapolated this trend to conclude that at sufficient depth, life would vanish entirely. The azoic hypothesis was widely accepted for decades. It seemed logical, it seemed consistent with the data, and it was profoundly, catastrophically wrong. In 1872, the British research vessel HMS Challenger set out on a 4-year expedition to survey the world's oceans. The Challenger expedition, which ran until 1876, covered roughly 130,000 kilometers of ocean and conducted deep-sea dredges and soundings at hundreds of stations around the globe. The expedition discovered life at every depth it sampled, including depths far exceeding Forbes's proposed azoic boundary. It recovered thousands of previously unknown species from the deep ocean, fundamentally overturning the azoic hypothesis and establishing the field of deep-sea biology in a single, comprehensive stroke. The Challenger expedition also made the first sounding of the Mariana Trench in 1875, recording a depth of over 8,000 meters at a point that would later be named Challenger Deep in the ship's honor. The deep ocean was not dead, it was teeming, and human science had been wrong about it for decades. This pattern has repeated itself with disturbing regularity. In the 1950s, scientists believed that the deep-sea floor was a monotonous, flat, featureless expanse of sediment. Then mid-ocean ridges were discovered, vast mountain ranges that circle the globe like the seams on a baseball, rising thousands of meters above the surrounding seafloor. In the 1960s, scientists believed that all life on Earth depended ultimately on energy from the sun, channeled through photosynthesis into the base of the food chain. Then hydrothermal vent communities were discovered in 1977, revealing entire ecosystems that derived their energy from the chemical compounds in volcanic fluids, completely independent of sunlight. In the 1980s, scientists believed the giant squid was likely extinct or extremely rare. Then, in 2004, Japanese researchers Tsunemi Kubadera and Kyoichi Mori photographed a living giant squid in its natural habitat for the first time, at a depth of approximately 900 meters. The creature was alive, active, and aggressive, attacking the bait and becoming entangled in the camera line. Each of these discoveries followed the same pattern. An assumption was made based on limited data. The assumption became established scientific opinion. New data arrived and overturned the assumption. And in each case, the new reality was stranger, more complex, and more rich than the old assumption had predicted. The deep ocean has never turned out to be simpler than we thought. It has always turned out to be more complicated, more populated, more active, more full of surprises. This historical pattern is directly relevant to the bloop, because it challenges the confidence with which any explanation for the sound can be offered. The icequake hypothesis is the current best explanation, but history teaches us that current best explanations for deep ocean phenomena have a track record of being incomplete, insufficient, or simply wrong. This does not mean we should reject the icequake hypothesis. It means we should hold it lightly, with the awareness that the ocean has embarrassed our certainties before and may do so again. The physics of the bloop also merit deeper examination. When NOAA first released the audio recording of the bloop to the public, the sound had been sped up 16 times from its original frequency. This was necessary because the bloop's primary energy was concentrated well below the range of human hearing. The human ear can detect sounds in the frequency range of roughly 20 to 20,000 Hz. The Bloop's dominant frequencies were below 20 Hz, in the infrasonic range. At these frequencies, the sound waves have wavelengths of 75 meters or more. They are pressure fluctuations so slow and so long that the human eardrum cannot vibrate in response to them. We cannot hear them, but we can sometimes feel them, as a deep, unsettling vibration in the chest, or a sense of unease that seems to have no source. Infrasound has been associated with feelings of dread and disorientation in humans. Some researchers have speculated that infrasonic vibrations may be responsible for some reports of haunted houses or supernatural encounters, as the low-frequency vibrations cause physiological responses that the brain interprets as fear or the presence of something unseen. The ocean is rich in infrasonic sound, seismic activity, whale communication, ice dynamics, and even the interaction of large waves with the ocean surface all produce infrasonic signals. The deep sound channel is particularly efficient at transmitting these frequencies because of their long wavelengths. A sound at 20 Hz has a wavelength of approximately 75 meters in seawater. A sound at 10 Hz has a wavelength of approximately 150 meters. These wavelengths are so long that they interact with the ocean's thermal and pressure gradients in ways that keep them confined to the sound channel with minimal loss. This is why the Bloop, despite originating in the remote southern Pacific, was detectable more than 5,000 kilometers away. The combination of infrasonic frequency and the deep sound channel created conditions for efficient long-range propagation. But the efficiency of propagation also makes it harder to estimate the true power of the source. The deep sound channel acts as a focusing mechanism, concentrating acoustic energy along a narrow depth band rather than allowing it to spread in all directions. This means that a sound detected at a great distance through the sound channel may be louder at the receiver than the same sound would be if it had traveled the same distance through open water without the channel's focusing effect. The implication is that the Bloop may have been somewhat less powerful at its source than the raw detection data would suggest. Somewhat, not dramatically. The distance of detection and the energy implied are still far beyond what most known sources can produce. But the uncertainty introduced by the sound channel's focusing properties adds yet another layer of ambiguity to the analysis. There is also the question of the Bloop's precise location. Triangulation using multiple hydrophones can determine the general area of a sound's origin, but the precision of the estimate depends on several factors: the number of receiving stations, the geometry of their arrangement, the accuracy of the arrival time measurements, and the accuracy of the sound speed model used for the intervening water. For a signal detected by an array of hydrophones designed to track submarines in the North Pacific and North Atlantic, the accuracy of triangulation for a source in the remote southern Pacific may have been limited. The Bloop's estimated coordinates should be understood as an approximate location rather than a precise one. This matters because it affects the plausibility of various hypotheses. If the location is accurate to within, say, 50 kilometers, the range of possible sources in that area is different from what it would be if the location is accurate to within 500 kilometers. Different geological features, different ice conditions, different biological habitats fall within different radii of uncertainty. The summer of 1997, when the Bloop was detected, was a period of significant oceanographic interest for another reason entirely. That year saw the development of a strong El Niño event, one of the most powerful of the 20th century. El Niño is a periodic warming of the eastern Pacific Ocean that disrupts normal weather patterns across the globe. It is driven by changes in the trade winds and the upwelling of deep cold water along the South American coast. During a strong El Niño, ocean temperatures, current patterns, and atmospheric circulation are all significantly altered. These changes affect everything from rainfall patterns in Southeast Asia to the distribution of fish populations off the coast of Peru. Could the El Niño of 1997 have contributed to the Bloop? The question is speculative, but not unreasonable. Changes in ocean temperature and current patterns could affect ice dynamics in the Southern Ocean, potentially triggering unusual calving events. Changes in ocean temperature could also affect the behavior and distribution of marine organisms potentially driving unusual species into unusual areas or triggering unusual vocalizations. And changes in the physical properties of the water column could alter the acoustic environment, changing the way sounds propagate and potentially amplifying sounds that would normally be inaudible at the distances involved. None of these possibilities has been demonstrated for the Bloop specifically, but they illustrate the complexity of the oceanic environment and the number of variables that must be considered when attempting to explain any single acoustic event. The El Niño connection is particularly worth considering because it suggests a temporal dimension to the mystery that is often overlooked. The Bloop was detected during a period of exceptional oceanographic disturbance. The 1997 to 1998 El Niño was one of the strongest on record, with sea surface temperature anomalies exceeding 4 degrees Celsius in parts of the eastern Pacific. This event disrupted marine ecosystems from the Galapagos Islands to the coast of California, causing massive die-offs of marine organisms in some areas and unusual species appearances in others. Seabirds that normally nested in the tropics were found thousands of kilometers north of their usual range. Fish species from warm waters appeared off the coasts of Oregon and Washington. The entire Pacific ecosystem was in a state of upheaval. Coral reefs bleached on a global scale. Upwelling patterns shifted, redirecting nutrient flows and altering the distribution of plankton, the foundation of the marine food web. The ripple effects extended from the surface to the deep, touching every layer of the water column. In such conditions, the baseline assumptions that underpin our understanding of normal ocean acoustics may not apply. A sound that seems inconsistent with known sources under normal conditions might be perfectly consistent with unusual phenomena driven by exceptional environmental disturbance. An iceberg that would not normally drift to the Bloop's coordinates might be carried there by anomalous currents. A marine organism that would not normally vocalize in a particular manner might be driven to do so by changes in food availability, water temperature, or population density. An underwater geological feature that would not normally produce detectable sounds might be activated by changes in deep water circulation patterns. The El Niño does not explain the Bloop, but it reminds us that the ocean is not a static system, and that events occurring during periods of environmental upheaval may not have straightforward explanation rooted in normal conditions. The Bloop was also detected during a period when the technology for listening to the ocean was itself undergoing rapid change. The transition of the SOSUS network from military to civilian use was still relatively recent. The techniques for processing and analyzing underwater acoustic data were evolving. New algorithms for separating biological signals from geological noise were being developed, and the catalogue of known ocean sounds, while extensive, was being expanded almost monthly as new data flowed in from the newly available hydrophone arrays. In this context, the detection of unidentified sounds was not unusual. What was unusual was the Bloop's power, its distinctiveness, and its resistance to classification even after detailed analysis by experts with decades of experience. The core problem of the Bloop is, ultimately, a problem of knowledge, not a problem of physics, not a problem of biology, a problem of how much we know about the ocean and how confident we can be in our conclusions given how little that is. The ocean is a system of staggering complexity. Its acoustic environment is shaped by temperature, pressure, salinity, topography, biological activity, ice dynamics, seismic activity, and human activity, all operating simultaneously and interacting in ways that are difficult to model and impossible to observe comprehensively. The Bloop was a single event within this system. It lasted 1 minute, it occurred once, and it was recorded by instruments that were designed for a different purpose, positioned in locations chosen for strategic rather than scientific reasons, and operating at a time when our understanding of the ocean's acoustic landscape was far less developed than it is today. In a well-explored, well-understood environment, the most likely explanation is usually the correct one. In a poorly explored, poorly understood environment, the most likely explanation is simply the least surprising guess. The distinction matters because it determines how seriously we take the residual uncertainty, and whether we continue to investigate or declare the matter resolved. The bloop, for now, remains in a grey zone, officially explained, unofficially unresolved. A sound from the deep that rose and fell and vanished, leaving behind a spectrogram that looks like a question mark drawn in frequency against a background of permanent darkness. It was heard once, or rather, a few times over one summer, and then the ocean swallowed whatever made it, returning to the vast, impenetrable silence that has characterized the abyss since long before any human ear was pressed against any instrument to listen. The mystery does not end with the bloop. It expands outward, like the pressure wave of the sound itself, into the broader landscape of the unknown deep, and the deeper one follows that expansion, the more apparent it becomes that the bloop was not an anomaly. It was a symptom of a planet that is mostly water, mostly dark, mostly unexplored, and mostly silent in ways that our instruments cannot yet break. But here is what makes this truly terrifying. The bloop is not the only question mark. It is not even the most troubling one. The deeper we look into the ocean's acoustic record, and the wider we cast our net across the landscape of deep-sea mysteries, the more we discover that the things we do not understand vastly outnumber the things we do. The icequake hypothesis for the bloop has become the default explanation in most popular accounts. Search for the bloop online, and the first result will almost certainly tell you it was ice. Case closed, mystery solved. But the reality is considerably more complicated, and the deeper one examines the various attempts to explain the bloop and its companion sounds, the more one realizes that our understanding of the deep ocean's acoustic landscape is far less complete than we tend to assume. The bloop was just the most famous entry in a catalogue of mysteries, and the explanations offered for these mysteries, while scientifically respectable, share a common limitation. They are hypotheses, not confirmed solutions. Each one has strengths, each one has weaknesses, and none of them has been verified by direct observation of the source. Let us begin with the icequake hypothesis, which deserves the most detailed examination because it is the most widely cited. The argument runs as follows. Large-scale ice fracturing in and around Antarctica produces immense amounts of acoustic energy. When an ice shelf calves, releasing an iceberg that may weigh millions or even billions of tons, the fracturing of the ice generates low-frequency sound waves that propagate through the ocean for thousands of kilometers. The spectral profile of these events can vary widely, depending on the specific characteristics of the fracture, the size of the ice mass, the depth of the water beneath it, the temperature of the surrounding ocean, and the geometry of the crack itself. Some icequakes produce sounds that, when analysed on a spectrogram, display a rising frequency pattern that bears a resemblance to the bloop's distinctive upward sweep. Therefore, the bloop is most likely an icequake. This explanation is plausible. It is parsimonious, meaning it does not require the existence of any unknown creature or undocumented geological process. It uses known phenomena to explain an observed event. And for many scientists and commentators, that is sufficient. But here is the problem. The icequake hypothesis, while plausible, rests on a form of reasoning by elimination rather than positive identification. Researchers did not identify a specific calving event that produced the bloop. They did not match the bloop's waveform to a recorded event at a known ice shelf on a known date. They did not find satellite imagery showing a major calving event at the bloop's approximate coordinates at the time of detection. What they demonstrated was that icequakes, as a general category of acoustic events, can produce sounds with some spectral characteristics similar to the bloop. This is a weaker claim than it might first appear. It is the difference between saying, this fingerprint matches a specific individual, and this fingerprint is consistent with the type of prints left by people who work in construction. Both statements convey useful information, but they carry very different levels of evidentiary weight. Several researchers have noted additional complications with the ice hypothesis. The bloop's point of origin, while in a region where icebergs are present, was not in a region known for the massive calving events that would be required to generate the observed signal strength. The major Antarctic ice shelves, the Ross, the Ron Filchner, the Larsen, are all situated along the Antarctic coastline, over 1,500 kilometers south of the bloop's estimated coordinates. Icebergs do drift northward from these shelves, carried by currents and wind. Large tabular icebergs have been tracked thousands of kilometers from their points of origin. It is entirely possible that such an iceberg reached the Bloop's vicinity and then fractured in a way that produced the recorded signal. But this scenario requires a specific chain of events: the calving of a large berg, its northward drift to the right location, and its subsequent fracturing at the right time, none of which have been independently verified. Furthermore, the Bloop's acoustic profile differed from many documented icequake recordings in subtle but potentially important ways. The Bloop's frequency rise was smoother and more gradual than the abrupt, jagged patterns typical of many ice fracture events. The duration of approximately 1 minute placed it at the longer end of documented icequake signals, and the Bloop's signal-to-noise ratio, the clarity of the sound relative to the background ocean noise, was unusually high for a single calving event. These differences do not rule out ice as the source. They simply indicate that if the Bloop was an icequake, it was an unusual one, and an unusual icequake is, almost by definition, harder to confirm than a typical one. The second hypothesis that received sustained scientific attention was biological origin. This is the explanation that caught fire in the public imagination, and the one that, despite being largely set aside by the scientific mainstream, continues to generate discussion and debate. The case for a biological source rests on several observations. First, the Bloop's spectral profile. The shape of its frequency contour over time resembled biological calls more closely than it resembled most geological events. Biological sounds in the ocean tend to show smooth, modulated patterns, while geological sounds tend to be more abrupt and broadband. The Bloop was smooth and modulated. Second, the Bloop's frequency range overlapped with the known vocalization frequencies of several large marine species, particularly the baleen whales, which communicate using low-frequency calls that can travel enormous distances through the deep sound channel. Third, the pattern of occurrence, repeated detections over a limited period, followed by permanent silence, is consistent with the behavior of a migratory animal that vocalized for a season and then moved on. The numbers are striking when we examine what a biological source would require. A blue whale, the largest known animal, measures roughly 30 meters in length, weighs up to 170 tons, and produces calls reaching approximately 188 decibels. To produce a sound of the Bloop's estimated amplitude, an organism would need to be substantially larger than a blue whale, though the exact size is difficult to calculate because it depends on assumptions about the animal's anatomy, the mechanism of sound production, and the efficiency of coupling between the sound-producing structures and the surrounding water. Some rough estimates have suggested an organism on the order of 60 to 90 meters in length, though these numbers are highly uncertain. For context, the longest animal known from the fossil record is thought to have been considerably shorter than that. The biological hypothesis faces several additional challenges beyond the size question. Any animal large enough to produce the Bloop would require enormous quantities of food. It would produce waste products. It would leave traces of its passage, shed skin cells, parasites, mucus, fecal matter that could be detected by other organisms or by scientific instruments. It would have a skeleton that, upon death, would sink to the ocean floor and potentially be discovered by deep-sea surveys. The absence of all of these forms of evidence weighs heavily against the biological hypothesis. It is not impossible that a large, unknown marine animal exists in the deep southern ocean without leaving any detectable trace, but the probability is considered extremely low by the vast majority of marine biologists. There is, however, an important caveat. The absence of evidence is meaningful only in proportion to the thoroughness of the search. In a well-surveyed environment, absence of evidence is a strong indicator of absence. In a poorly surveyed environment, it is a much weaker one. The deep southern ocean is among the least surveyed marine environments on Earth. The number of deep-sea surveys conducted in the Bloop's region of origin can be counted on a small number of hands. The seafloor has not been systematically searched. The water column has not been systematically monitored. And the biological communities of the deep southern ocean, at depths below 2,000 meters, are among the least studied on the planet. In this context, the absence of physical evidence for a large unknown organism is less conclusive than it would be in, say, the well-studied waters of the North Atlantic or the Mediterranean. The third hypothesis considered was geological in nature, specifically related to submarine volcanic activity or tectonic movement. The ocean floor, particularly in the Pacific, is geologically active on a grand scale. The East Pacific Rise, a major mid-ocean spreading ridge, runs through the general region of the Bloop's origin. Along this ridge, tectonic plates are pulling apart, and new oceanic crust is being formed by volcanic activity along the rift. Hydrothermal vents, underwater volcanoes, and seismic events are common features of this environment. Could the Bloop have been produced by a unique volcanic or tectonic event? A previously undocumented type of submarine eruption? A sudden, catastrophic movement along a fault line? The geological hypothesis has some appeal. It does not require unknown organisms. It operates within the framework of known geophysical processes. And the general area of the Bloop's origin is indeed geologically active. But the Bloop's spectral characteristics did not match the standard profiles of earthquake T-phases, which are the acoustic signals generated by seismic events that propagate through the ocean's deep sound channel. Earthquake T-phases typically have sharper onsets, broader frequency distributions, and shorter durations than the Bloop. Volcanic eruptions can produce a wider variety of sounds, including some with more complex frequency patterns, but they are generally accompanied by other observable phenomena. Changes in water chemistry, thermal anomalies detectable by satellite, plumes of volcanic material that can be observed by remote sensing instruments. No such accompanying evidence was detected at the time of the Bloop. It is worth noting that our catalogue of submarine geological sounds is itself incomplete. The ocean floor hosts geological processes that have no direct equivalent on land. The interaction of magma with deep-sea water, the fracturing of newly formed oceanic crust under the stress of tectonic forces, the collapse of submarine volcanic structures, the sudden release of pressurized fluids from beneath the seafloor, all of these processes produce sounds, and not all of them have been comprehensively recorded and catalogued. The geological hypothesis for the Bloop, while not well supported by existing data, cannot be entirely ruled out on the basis of existing data, because the existing data does not cover all the geological sounds the ocean can produce. A fourth angle of investigation involves ocean current dynamics and their interaction with undersea topography. The Southern Ocean is home to the Antarctic circumpolar current, the most powerful ocean current on Earth. This current carries an estimated 135 million cubic meters of water per second in its continuous circuit around Antarctica, driven by the prevailing westerly winds and constrained by the narrow Drake Passage between South America and the Antarctic Peninsula. When this immense flow of water encounters obstacles on the seafloor, ridges, seamounts, narrow channels between geological features, the resulting turbulence can generate low-frequency sounds of considerable power. The phenomenon is analogous to the way wind whistling through a narrow gap in a building can produce a loud, sustained tone. In the ocean, the medium is water rather than air. The gap is a geological feature on the seafloor, and the resulting sound is typically in the infrasonic range. Could the Bloop have been produced by a transient interaction between the Antarctic circumpolar current and an underwater topographic feature? Perhaps a temporary change in current velocity or direction caused the flow over a particular seamount or ridge to produce a resonant sound that was then amplified by the deep sound channel. This hypothesis is speculative, but it is not without scientific basis. Current-generated sounds have been documented in several ocean environments, though they tend to be relatively steady and continuous, rather than discrete events with clear beginnings and endings. The Bloop's discrete, 1-minute duration is not consistent with a sustained current flow, but it could potentially be consistent with a brief, transient change in current conditions, a pulse or eddy that interacted with a specific topographic feature for a limited period before dissipating. Verifying this hypothesis retroactively would require detailed knowledge of the current conditions and seafloor topography at the Bloop's precise coordinates at the time of detection, data that simply does not exist. A fifth and less frequently discussed hypothesis involves the acoustic properties of the ocean itself as a medium. The deep sound channel, as described earlier, acts as a natural waveguide that can focus and amplify sounds over enormous distances. But the channel is not uniform. Its depth, width, and efficiency vary with local water conditions. Temperature, salinity, and pressure all affect the speed of sound, and therefore the channel's focusing properties. In some regions, particularly where different water masses converge, or where strong temperature gradients exist, the acoustic environment can become highly complex, with multiple sound channels, acoustic shadow zones, and regions of enhanced focusing. It is theoretically possible that the Bloop was not as powerful at its source as the recording data suggests. If the sound was generated in a region where the local acoustic environment happened to be particularly efficient at focusing energy into the deep sound channel, a relatively modest source could have produced a disproportionately powerful signal at the distant hydrophones. This is the acoustic equivalent of a whispering gallery, where a whisper at one focal point becomes clearly audible at another focal point far away, despite the distance. Under this hypothesis, the Bloop might have been produced by a perfectly ordinary source, a moderate-sized iceberg fracturing, a common marine animal vocalizing, a small geological event that was amplified by favorable acoustic conditions beyond its natural reach. This would elegantly resolve the paradox of the Bloop's enormous apparent power while maintaining consistency with known sources. The acoustic amplification hypothesis is attractive, but it faces the same fundamental problem as the others. It is difficult to test. Constructing an accurate model of the acoustic environment at a specific location in the remote Southern Ocean at a specific time in 1997 would require data on water temperature, salinity, and density at multiple depths along the propagation path, data on the seafloor topography in the source region, and data on the configuration of the deep sound channel between the source and each receiving hydrophone. Most of this data does not exist. The Southern Ocean is among the most poorly instrumented bodies of water on Earth, and oceanographic measurements from a specific date in 1997 are extremely sparse for the region in question. Each of these 5 hypotheses, ice calving, biological origin, geological event, current topography interaction, and acoustic amplification, offers a pathway toward explaining the Bloop. Each has internal logic, each is consistent with at least some aspects of the available data, and each has limitations that prevent it from being confirmed. The scientific community, presented with this array of possibilities and unable to conduct direct observation of the source, has gravitated toward the icequake explanation as the most parsimonious and most consistent with the available evidence. This is reasonable scientific practice. When multiple hypotheses are compatible with the data, the simplest one is preferred. But parsimony is a heuristic, not a guarantee of truth. And in a domain as poorly explored as the deep Southern Ocean, the simplest explanation may simply be the least imaginative one. The mystery extends beyond the Bloop itself into the broader catalogue of deep ocean phenomena that resist easy categorization. Consider the case of hydrothermal vent ecosystems, which represent one of the most profound biological discoveries of the 20th century. In 1977, the research submersible Alvin descended to the Galapagos Rift and discovered thriving communities of organisms clustered around volcanic vents on the seafloor at depths exceeding 2,500 meters. Giant tube worms, some exceeding 2 meters in length, dense colonies of clams and mussels, clouds of shrimp, and thick mats of bacteria covered the rocks around the vents. The water emerging from the vents was superheated, reaching temperatures of over 350 degrees Celsius, and laden with dissolved chemicals including hydrogen sulfide, methane, and various metals. The organisms clustered around these vents were deriving their energy not from sunlight, but from the chemical compounds in the vent fluid, through a process called chemosynthesis. This was a completely new category of ecosystem, independent of the photosynthetic food chain that supports virtually all life on the surface. Its discovery fundamentally altered the definition of what constitutes a habitable environment. Since 1977, hundreds of hydrothermal vent sites have been discovered along mid-ocean ridges and other geologically active regions of the seafloor. Each one hosts a distinct community of organisms, many of them found nowhere else on Earth. The diversity is staggering. Pompeii worms that survive temperatures of over 80 degrees Celsius, yeti crabs that cultivate gardens of bacteria on their hairy claws, scaly foot gastropods, snails that incorporate iron sulfide into their shells, effectively armoring themselves in metal. Each of these organisms represents an evolutionary solution to the extreme conditions of the deep sea that was completely unknown before the vent systems were explored. And the total number of vent sites that have been explored in detail is a tiny fraction of the estimated number that exist. Most mid-ocean ridges have not been surveyed for vent activity. The vents that have been studied are concentrated in a few well-explored areas: the East Pacific Rise, the Mid-Atlantic Ridge, the Western Pacific back arc basins. The rest remain unknown. Then there are brine pools, one of the most surreal features of the deep ocean. Found on the floor of the Gulf of Mexico, the Mediterranean Sea, and the Red Sea, brine pools are bodies of water so concentrated with dissolved salt that they form a distinct layer at the bottom of the ocean, complete with a visible surface, shorelines, and even waves. The salinity of these pools can be 3 to 8 times higher than the surrounding seawater. The density difference between the brine and the normal seawater is so great that the boundary between them is as sharp and defined as the boundary between a lake and its shoreline on land. Animals that fall into brine pools often go into toxic shock and die. The edges of the pools are littered with the carcasses of crabs, fish, and other organisms that wandered too close. And yet, specialized organisms thrive at the margins of these toxic lakes, feeding on the chemical energy released by the interaction between the brine and the surrounding water. This is not science fiction. These are documented features of the Earth's ocean floor, photographed and filmed by submersibles and remotely operated vehicles. Consider also the deep-sea creatures that seem to defy the physical constraints of their environment. The barrel-eye fish, with its transparent, fluid-filled head and upward-pointing tubular eyes, looks like a creature designed by an artist rather than shaped by natural forces. The vampire squid, which lives at depths of 600 to 1,200 meters, and is neither a squid nor an octopus, but a member of its own distinct order, responds to threats by inverting its webbed arms over its body to reveal rows of fleshy spines, transforming itself into a spiky ball of darkness. The Dumbo octopus, found at depths exceeding 4,000 meters, propels itself through the water by flapping ear-like fins on either side of its mantle, drifting through the abyss like a ghostly, translucent bell. Each of these organisms was unknown to science until relatively recently. Each represents a form of life that defies easy prediction based on the biology of surface organisms, and each was discovered by chance, during surveys that covered only a minuscule fraction of the deep-sea environment. The Yonaguni Monument, discovered off the coast of Yonaguni Island, Japan, in 1986, adds another dimension to the catalogue of deep ocean enigmas. This massive underwater rock formation features structures that appear to include flat terraces, sharp right angles, stairway-like features, and what some observers have described as carved pillars. The geologist Masaki Kimura of the University of the Ryukyus spent years studying the formation and concluded that it bore evidence of human construction, possibly dating to a period when sea levels were significantly lower and the structure would have been above water. Other geologists, notably Robert Schoch of Boston University, have argued that the formation is entirely natural, produced by the fracturing of sandstone along natural planes of weakness and the erosion of softer layers. The debate has continued for decades, and no consensus has been reached. The monument remains an enigma, a structure that looks artificial but might be natural, or might be natural but looks artificial, sitting in shallow water off the coast of an island, neither fully explained nor fully dismissed. The accumulation of these mysteries, the bloop, the companion sounds, the hydrothermal vent ecosystems, the brine pools, the undiscovered species, the Yonaguni Monument, the unexplored trenches and seamounts, creates a picture that is at once humbling and disquieting. The ocean is not a place where human knowledge is nearly complete. It is a place where human knowledge is barely begun, and the confidence with which we declare individual mysteries solved should be tempered by the awareness that we are operating in an environment where our fundamental inventory of what exists is radically incomplete. Then something happened that changed everything. Not a single discovery, not a single sound, but a gradual accumulating realization. The realization that the gap between what we know about the ocean and what the ocean actually contains is not closing. It is, in some respects, widening. Every new tool we develop for exploring the deep, every new submersible, every new ROV, every new hydrophone array, every new genetic sampling technique reveals more unknowns than it resolves. The rate of discovery is accelerating, but the apparent size of the unknown is accelerating faster. We are not approaching a comprehensive understanding of the ocean. We are approaching a more accurate understanding of how much we do not know. This widening gap between knowledge and mystery is visible in almost every branch of deep ocean science. In marine biology, the discovery rate of new species shows no sign of slowing. Researchers estimate that between 700 and 2,000 new marine species are formally described each year, and the backlog of specimens awaiting classification in museum collections around the world runs to many thousands more. A single deep-sea trawl or ROV dive in an unexplored area routinely yields organisms that have never been documented. During a 2016 expedition to the Mariana Trench region, a team of researchers using a remotely operated vehicle observed a previously unknown species of snailfish swimming at a depth of approximately 8,178 meters, the deepest fish ever recorded at that time. The creature was small, pale, and translucent, with a body that seemed barely substantial enough to exist, and yet it was thriving in conditions that would destroy virtually any other vertebrate on Earth. The discovery was made by accident, during a survey that was focused on a different set of objectives entirely. How many similar organisms have been missed because no camera happened to be pointing at the right patch of ocean at the right moment? In marine acoustics, the catalogue of unidentified sounds continues to grow even as technology improves. Modern hydrophone arrays are more sensitive and more widely distributed than the Cold War-era SOSUS network that detected the Bloop. They record continuously, generating vast datasets that are analyzed by increasingly sophisticated software algorithms, and they continue to detect sounds that resist classification. In 2014, researchers detected a recurring sound in the Mariana Trench that they named the Western Pacific Biotwang, a complex call lasting between 2.5 and 3.5 seconds, comprising a low-frequency moan followed by a metallic, almost mechanical-sounding rising tone. The sound was detected at depths below 1,000 meters and occurred repeatedly over several months. After extensive analysis, the biotwang was tentatively attributed to a species of baleen whale, possibly a bride's whale or a minke whale, but the identification was not definitive, and the sound's unusual metallic quality remained unexplained. The deep ocean continues to produce new acoustic puzzles faster than we can solve the old ones. In submarine geology, the mapping of the ocean floor has advanced significantly since the era of the Bloop, but the overall picture remains one of profound incompleteness. The Nippon Foundation and the General Bathymetric Chart of the Oceans, an international collaboration known as GBCO, launched a project in 2017 with the goal of mapping the entire ocean floor by 2030. As of the most recent progress reports, less than a quarter of the ocean floor had been mapped with modern multi-beam sonar at the resolution necessary for meaningful scientific analysis. The remainder is known only through satellite-derived gravity data, which provides a rough topographic picture at a resolution of several kilometers, sufficient to identify major features like trenches and ridges, but completely inadequate for detecting smaller features like individual seamounts, hydrothermal vent fields, or submarine canyons. The ocean floor is quite literally less well-mapped than the surfaces of Mars and the Moon, both of which have been surveyed by orbital spacecraft to resolutions of meters or less. The implications of this mapping gap for the Bloop mystery are direct. If we do not know the detailed topography of the ocean floor in the region where the Bloop was detected, We cannot accurately model the acoustic environment. If we cannot accurately model the acoustic environment, we cannot confidently determine how the bloop signal was affected by propagation through the water column. And if we cannot determine that, we cannot accurately estimate the true power of the source or the distance it travelled. The entire chain of inference that leads to the icequake explanation depends on assumptions about the acoustic environment that are, in the specific region of the bloop, largely unverified. The deep ocean also conceals human artifacts and human tragedies that add a different kind of weight to the mystery of its depths. The ocean floor is littered with the wreckage of ships and aircraft that have been lost over the centuries, many of them never found. The case of Malaysia Airlines Flight 370, which disappeared on March 8, 2014, during a flight from Kuala Lumpur to Beijing with 239 people aboard, illustrates the ocean's capacity to conceal even large objects that are being actively searched for. Despite one of the most extensive and expensive search operations in aviation history, covering over 120,000 square kilometers of seafloor in the southern Indian Ocean, using state-of-the-art autonomous underwater vehicles, the main wreckage of the aircraft was not found. Only small pieces of debris, washed ashore on coastlines thousands of kilometers from the suspected crash site, confirmed that the aircraft had entered the ocean. The ocean swallowed the rest, completely, and a significant area of ocean floor was mapped in unprecedented detail during the search, revealing previously unknown seamounts, ridges, and canyons, but yielding no trace of the aircraft at its expected location. If the ocean can swallow a modern commercial airliner and resist discovery by a multinational search operation equipped with the best deep-sea technology available, the question of what else it might be concealing becomes less theoretical and more sobering. The Bermuda Triangle, that infamous region of the western North Atlantic, bounded roughly by Miami, Bermuda, and Puerto Rico, has been associated with mysterious ship and aircraft disappearances for decades. While the vast majority of these disappearances have mundane explanations, storms, navigational errors, equipment failures, human mistakes, a small number remain genuinely puzzling. The USS Cyclops, a United States Navy cargo ship, disappeared without a trace in March of 1918 while carrying 306 crew and passengers through the Bermuda Triangle region. No wreckage was ever found, no distress signal was sent, no bodies were recovered. The ship simply vanished. Nearly a century later, the Cyclops has never been located, despite the area being among the most heavily trafficked ocean regions on Earth. The Puerto Rico Trench, which forms the deepest part of the Atlantic Ocean at approximately 8,376 meters, runs along the northern edge of the Bermuda Triangle region. Wreckage that sinks to such depths is extraordinarily difficult to locate, even with modern technology. The pressure at the bottom of the Puerto Rico Trench exceeds 800 atmospheres. The darkness is total. The terrain is rugged and complex. An object the size of a large ship, compressed and corroded by decades or centuries in such conditions, would be nearly unrecognizable. The ocean does not merely hide things. It transforms them, it crushes them, it dissolves them, and it buries them under layers of sediment that accumulate with geological patience, millimeter by millimeter, over the span of centuries. These human stories of loss and disappearance in the deep ocean serve as a reminder that the bloop is not an isolated curiosity. It is one manifestation of a larger truth. The ocean is a domain of concealment. It hides biological organisms that we have not discovered. It hides geological features that we have not mapped. It hides acoustic phenomena that we have not catalogued. It hides human artifacts that we cannot find. And it does all of this not through any deliberate act of concealment, but simply by being what it is: vast, deep, dark, cold, and pressurized beyond the tolerances of human technology and human endurance. The math is striking when we step back and consider the full picture. The total volume of the ocean is roughly 1.35 billion cubic kilometers. The total volume of ocean that has been directly observed by any instrument, a submersible's camera, an ROV's lights, a diver's eyes, is an almost infinitesimal fraction of that total. If we generously assume that all deep-sea expeditions in history, combined, have directly observed a volume equivalent to a cube roughly 10 kilometers on each side, and that is a generous assumption, then the observed fraction would be less than 1/1,000,000th of the total ocean volume. We are not looking at a partially explored environment. We are looking at a virtually unexplored one that we have sampled at a handful of isolated points. This is the context in which the bloop must be understood, not as a solved puzzle, not as a debunked myth, but as a genuine signal from an environment that we do not comprehend. A sound whose source we have guessed at, perhaps correctly, perhaps not. A datum from a dataset so vast and so incomplete that any single datum is as likely to mislead as to illuminate. The bloop was a whisper from the abyss, and the abyss has much more to say than we have yet heard. The deep sea also challenges our understanding of what is physically possible for living organisms. In 2020, researchers analyzing sediment cores from the South Pacific found microbial life in sediments buried beneath the seafloor at depths of more than 100 meters below the ocean bottom, in material that was estimated to be more than 100 million years old according to geological dating models. These microbes were alive, not dormant, not fossilized, alive and metabolically active, surviving on vanishingly small quantities of energy, in conditions that were previously thought to be incompatible with any form of life. The discovery pushed the known boundaries of biology into territory that had previously been considered sterile. If life can persist in 100-million-year-old sediment beneath the seafloor, what else might be living in the vast unsampled volumes of the deep ocean proper? The accumulation of evidence from every branch of deep ocean science points to the same conclusion. Our knowledge is fragmentary. Our catalogues are incomplete. Our explanations, even the good ones, carry margins of uncertainty that are wider than we often acknowledge. The bloop sits at the center of this web of uncertainty, a single famous sound that became the public face of a much larger reality. The reality that the ocean, the largest and oldest environment on our planet, remains more mystery than knowledge. And every attempt to explain the bloop, whether through ice, biology, geology, ocean dynamics, or acoustic physics, eventually runs into the same wall. We do not know enough about the environment in which the sound was produced to be certain of our answer. Something is wrong with our assumptions about how well we know this planet. We assume that the age of discovery is over. We assume that the blank spaces on the map have been filled in. We assume that if something large and important existed on Earth, we would have found it by now. The deep ocean contradicts all of these assumptions. It is the largest blank space on Earth. It is growing more mysterious, not less, as our tools improve. And the bloop, that one rising note from the summer of 1997, is the sound of the map's edge, the boundary between what we know and what we do not. The place where confidence ends and wonder begins. Consider the sheer logistical reality of what comprehensive ocean exploration would require. The world's entire fleet of research-capable vessels numbers in the low hundreds. Many of these ships are aging, underfunded, and committed to ongoing monitoring programs that leave little capacity for new exploratory work. The number of deep-rated submersibles capable of reaching the abyssal plain, let alone the Hadal trenches, can be counted on two hands. The number of scientists trained to operate these vehicles and interpret the data they return is smaller still. We are attempting to understand the largest environment on our planet with a workforce and a toolkit that would be considered inadequate for surveying a medium-sized national park. The mismatch between the scale of the question and the scale of our effort to answer it is not subtle, it is overwhelming, and there are more sounds, always more sounds. The ocean produces acoustic phenomena that defy comfortable explanation on a regular basis. In 2012, an array of hydrophones deployed in the Arctic Ocean detected a series of pings emanating from the seafloor of the Fury and Hecla Strait in the Canadian territory of Nunavut. Local Inuit hunters had reported hearing the pinging sounds for months and noted that marine wildlife seemed to be avoiding the area. The Canadian military investigated and found no anthropogenic source. The sounds remained unexplained for years before being tentatively attributed to natural phenomena, though the specific mechanism was never conclusively identified. The ocean, both in the Arctic and in every other basin, is a noisemaker of prodigious range and creativity. producing sounds that surprise even the researchers whose entire careers are devoted to listening. There is also the phenomenon of deep-sea methane seeps and the explosive release of methane hydrates from the seafloor, which represents yet another potential mechanism for producing unusual and powerful ocean sounds. Methane hydrate, sometimes called fire ice, is a crystalline solid in which methane gas is trapped within a lattice of water molecules under conditions of high pressure and low temperature. Vast deposits of methane hydrate exist beneath the ocean floor along continental margins and beneath Arctic permafrost. Under certain conditions, a change in bottom water temperature, a submarine landslide, a seismic event, these deposits can become destabilized, releasing enormous quantities of methane gas in a sudden explosive eruption from the seafloor. Such an event would produce a powerful acoustic signal. The frequency and spectral characteristics of that signal would depend on the volume of gas released, the depth of the release, the geometry of the seafloor, and the properties of the water column above. No one has proposed methane hydrate destabilization as a specific explanation for the bloop, but the existence of this mechanism illustrates how many potential sound sources exist in the deep ocean that have not been comprehensively studied or catalogued. Methane seeps have also been implicated in one of the more provocative theories about ship disappearances in the ocean. The idea, proposed by several researchers over the years, is that a sudden, massive release of methane gas from the seafloor could create a localized reduction in water density, sufficient to cause a ship to lose buoyancy and sink rapidly, without warning and without time to send a distress signal. Laboratory experiments have demonstrated that a sufficient concentration of gas bubbles in water can indeed reduce its density to the point where floating objects sink. Whether this mechanism has ever actually sunk a real ship in a real ocean remains unproven, but the theory illustrates the range of powerful, dangerous, and poorly understood processes occurring beneath the ocean surface at any given moment. The deep ocean also hosts chemical environments that have no equivalent anywhere on the surface of the Earth. In the eastern Mediterranean, at a depth of roughly 3,500 meters, researchers have discovered anoxic basins, enclosed depressions in the seafloor filled with water that contains no dissolved oxygen and is rich in hydrogen sulfide and other toxic compounds. These basins are essentially underwater lakes of poison, and yet they support unique microbial communities that have adapted to survive in conditions that would kill virtually any multicellular organism. The boundaries between these toxic basins and the normal surrounding seawater are as sharp and well defined as the boundary between oil and water in a glass. Living organisms cluster along these boundaries, exploiting the chemical energy gradient in much the same way that plants exploit the light energy gradient at the Earth's surface. Each new discovery in the deep ocean, each new sound, each new organism, each new chemical environment, each new geological feature adds another layer to the picture, and the picture that emerges is not one of a well-understood environment with a few remaining gaps. It is one of an environment that remains fundamentally mysterious, where the gaps in our knowledge are larger than the islands of what we know. The bloop emerged from this environment. It was heard by instruments that were listening to a tiny fraction of the ocean. It was analysed by scientists who were working within a framework of knowledge that covered a small portion of the possible sources, and it was explained by a hypothesis that, while plausible, has not been confirmed by direct observation of the source event. This does not mean the explanation is wrong. It may be entirely correct. Ice may have been the source. But the honest accounting of what we know and what we do not know compels a degree of humility that is often missing from popular accounts of the bloop. The ocean produced a sound. We heard it, we guessed what made it, and we moved on. The ocean, meanwhile, continued doing whatever it was doing in the dark, at the bottom, in the cold, at the pressure of 1,000 atmospheres, in the places where no human has ever been and no instrument has ever reached. Whatever made the bloop, the ocean knows. We are still learning to ask the right questions. There is a number that every person should know, but almost no one does. It is a number that, once it settles into the mind, changes the way you think about the planet you live on. The number is 95, 95%. That is the estimated proportion of the ocean that remains unexplored. Not unexplored in the sense that no one has sailed across the surface. Unexplored in the sense that no human eye, no camera, no submersible, no instrument of any kind has ever visited or directly observed the conditions at that location. 95%. To put it differently, for every 1 square kilometre of ocean floor we have seen, there are roughly 19 square kilometres we have not. And the ocean floor covers more area than all the land on Earth combined. Let that sink in. We live on a planet that is mostly ocean. We call it Earth, but it is, by any reasonable measure, a water world. The land we inhabit, the continents and islands where all of human history has unfolded, represents less than 30% of the planet's surface. The rest is water, deep water, dark water, water that presses down with the weight of mountains, water that has not been touched by sunlight since before the first human civilization arose, and we have explored less than 5% of it. This statistic is so frequently cited that it has begun to lose its impact through repetition. But consider what it actually means. If you were reading a book that was 200 pages long, 5% would be 10 pages. Imagine forming a confident opinion about the book's plot, its characters, and its themes based on 10 pages chosen from random locations throughout the text. That is approximately the level of confidence we are entitled to when we make claims about the contents and processes of the deep ocean. This is not a failure of ambition. It is a consequence of physics. The deep ocean is one of the most hostile environments accessible to human beings. The pressure at moderate depths is sufficient to crush a human body in seconds. The cold saps heat from any warm object with ruthless efficiency. The darkness is absolute and unbroken, and the distances involved are staggering. The ocean is not a single entity that can be surveyed from a single vantage point. It is a vast three-dimensional space, and exploring it requires moving through that space slowly, methodically, and at enormous expense. A single deep-sea expedition using a manned submersible can cost millions of dollars and yield data from only a few square kilometers of seafloor. An entire research cruise, lasting weeks and involving dozens of scientists and crew, might thoroughly investigate a patch of ocean floor no larger than a city block. Unmanned vehicles are cheaper but slower, and their range is limited by battery life and communication bandwidth. Satellite mapping can reveal the gross topography of the ocean floor through gravitational anomalies detected from orbit, but it cannot resolve features smaller than a few kilometers across. For true exploration, the kind that reveals new species and new phenomena and new sounds, there is no substitute for being there, and we are almost never there. The implications of this are profound. When a scientist says the bloop was probably caused by ice, that scientist is making a statement within a framework of knowledge that covers less than 5% of the relevant domain. The icequake hypothesis is based on comparisons with known icequake recordings, but the catalogue of known icequake recordings is itself incomplete. It is drawn from the limited number of locations where hydrophones have been deployed for the limited number of years they have been operating. The possibility that the bloop was caused by a process we have not yet documented, a process that occurs in the 95% of the ocean we have not explored, cannot be dismissed with confidence. It can only be acknowledged as less likely than the known alternatives, which is a very different thing from saying it has been ruled out. More humans have walked on the surface of the moon than have visited the deepest point of the ocean. This is not a metaphor. It is not an exaggeration. It is a literal, verifiable fact. The moon is approximately 384,000 kilometers away. The deepest point of the ocean is approximately 11 kilometers below the surface of the water. And yet, in terms of the number of human visitors, the moon wins. 12 people walked on the lunar surface during the Apollo program between 1969 and 1972. As of the most recent counts, fewer people than that have reached the bottom of Challenger Deep in the Mariana Trench. The first manned descent to Challenger Deep was accomplished on January 23, 1960, by Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh aboard the bathyscaphe Trieste. They descended to a depth of approximately 10,916 meters and spent roughly 20 minutes at the bottom before ascending. The viewport of their pressure sphere had cracked during the descent. The sediment they're landing stirred up reduced visibility to nearly zero. They saw almost nothing, and no human returned to that depth for more than 50 years. In 2012, filmmaker James Cameron made a solo descent in the Deep-Sea Challenger submersible, reaching a depth of approximately 10,008 meters. He spent roughly 3 hours at the bottom, collecting samples and filming the landscape. It was only the second manned descent to the deepest point on Earth, more than half a century after the first. A small number of additional descents have been made in subsequent years using the submersible limiting factor, designed by Triton submarines and piloted by explorer Victor Vescovo, who completed a series of record-breaking dives to the deepest points in all 5 of the world's oceans. But the total number of people who have personally witnessed the deepest point on Earth remains extraordinarily small. It is a number you could fit comfortably around a dinner table. The contrast between this and the resources humanity has devoted to exploring the sky above is staggering. We have launched thousands of satellites into orbit around the Earth. We have sent robotic probes to every planet in the solar system and several of their moons. We have landed rovers on Mars that have operated for years, traversing the Martian landscape and transmitting detailed photographs and chemical analyses back to Earth across a distance of hundreds of millions of kilometers. We have constructed space telescopes capable of observing galaxies billions of light years away and detecting the faint afterglow of the universe's formation. We have even sent a spacecraft beyond the boundary of the solar system itself, into the interstellar medium, a place so distant that radio signals traveling at the speed of light take more than 22 hours to reach us. The total investment in space exploration over the past 6 decades runs into the hundreds of billions of dollars across all nations. The total investment in deep ocean exploration, by contrast, is a fraction of that figure. Not a comparable fraction, a small fraction. The reasons for this disparity are complex and not entirely irrational. Space exploration captured the public imagination during the Cold War and became intertwined with national prestige and geopolitical competition. The space race between the United States and the Soviet Union produced political will and funding on a scale that ocean exploration has never enjoyed. There is also a visual dimension to the difference. Space is photogenic, rocket launches are dramatic, images of distant planets and nebulae are breathtaking. The deep ocean, by contrast, is dark. Photographs from the abyss tend to show grey sediment, pale creatures and murky water. The aesthetic disparity has real consequences for public interest and, by extension, for funding. We explore what excites us. And for most of human history, the sky has excited us more than the sea beneath our feet. But the consequence of this disparity is that the ocean, which covers most of our own planet and directly influences our climate, our weather, our food supply, the oxygen content of our atmosphere, and the carbon balance of our biosphere, receives a tiny share of the scientific attention and funding that we devote to studying places we cannot live and environments that have no immediate bearing on human survival. This is not merely an abstract inequity. It has practical consequences for our ability to understand and respond to changes in the ocean that directly affect billions of people. It also means that our baseline of knowledge, the foundation upon which we build our hypotheses and draw our conclusions about the ocean, is incomplete. Not slightly incomplete, massively incomplete. When we say the Bloop was probably ice, we are saying it based on the best available evidence, which was gathered from a tiny, unrepresentative sample of the total ocean acoustic environment. The hydrophones that detected the Bloop were positioned at a handful of locations in the Pacific and Southern Oceans. They listened at a specific depth. They were sensitive to a specific range of frequencies. They were operational for a specific window of time. Everything they recorded represents the acoustic activity of a minuscule sliver of the total ocean volume during a brief interval of geological time. The sounds they missed, the sounds produced in locations where no hydrophone was listening, at frequencies outside the range of the instruments, or during the decades before and after the monitoring period, are unknown and unknowable. The confidence we place in any conclusion about the ocean should be proportional to the completeness of our data, and our data is not complete. It is barely begun. Something is wrong with our assumptions about how well we know our own planet. We have constructed a narrative in which the Earth has been explored, mapped, and catalogued. We speak of the age of exploration as if it ended centuries ago, when the last coastlines were charted and the last continents named. We look at globes and atlases and see a world that is fully documented, every feature labelled, every border drawn. But this image is an illusion. It represents the surface, and the surface is only the beginning. The ocean, which covers 70% of that surface, extends downward for kilometers into a volume that dwarfs every terrestrial habitat combined. And most of that volume is as unexplored as any alien world. Consider the tools available for deep ocean exploration. The most capable manned submersibles can carry 2 or 3 people to depths of roughly 11,000 meters. They move slowly, typically at speeds of 1 to 3 knots. Their viewing windows are small, often no larger than a dinner plate, providing a cone of illumination that extends only a few meters into the surrounding darkness. Their lights, while powerful by terrestrial standards, are swallowed by the ocean after a few dozen meters in every direction. Their mission durations are measured in hours, not days. An entire dive to the bottom of the Mariana Trench and back takes the better part of a day, of which only an hour or 2 is spent at the maximum depth. The amount of ocean floor that can be observed during a single dive is vanishingly small, perhaps equivalent to the area of a large house. Unmanned remotely operated vehicles, or ROVs, can stay submerged longer and do not risk human lives, but they are tethered to a surface vessel by cables that can be thousands of meters long. These cables limit the ROV's range and mobility and make operations in rough weather or strong currents extremely difficult. The cable also serves as the communication link between the ROV and its operators, transmitting video and control signals in real time. If the cable fails, the ROV is lost. Despite these limitations, ROVs are the workhorse of modern deep-sea research, used for everything from biological surveys to geological sampling to the inspection of underwater infrastructure. Autonomous underwater vehicles, or AUVs, are untethered and can cover larger areas than ROVs, following pre-programmed routes through the deep ocean without a physical connection to the surface. They are the closest thing we have to deep-sea drones, but they carry limited sensor payloads. Their battery life restricts their range, and they must surface periodically to transmit data via satellite and recharge their power systems. An AUV can survey a larger area than a submersible or an ROV, but its surveys are typically conducted at altitude above the seafloor, and the resolution of its sensors decreases with distance. Detecting a new species, a small geological feature, or an unusual acoustic source from an AUV requires that the object of interest be directly in the vehicle's path and within the detection range of its instruments. In an ocean with a floor area of roughly 361 million square kilometers, the probability of an AUV stumbling upon any specific feature is extremely low unless the search is guided by prior information. None of these tools can survey the ocean at the scale required to claim comprehensive knowledge. The ocean is simply too big and too deep. To survey the entire ocean floor at the resolution necessary to detect individual organisms or small geological features would require an effort several orders of magnitude beyond anything currently planned or funded. It would be the largest scientific undertaking in human history, dwarfing the cost and complexity of the Human Genome Project, the Large Hadron Collider, and the James Webb Space Telescope combined. And it is not on any government's agenda. It is not on any international organization's roadmap. It is not even a serious topic of discussion in most policy circles. The deep ocean, despite being the largest and least understood environment on our own planet, does not have a constituency powerful enough to command the resources necessary for its systematic exploration. The monitoring gap extends beyond exploration to basic observation. The entire global network of deep ocean acoustic monitoring stations, the successor systems to the Cold War-era SOSUS arrays, covers a tiny percentage of the ocean's total area. There are vast stretches of the Indian Ocean, the Southern Atlantic, the Arctic, and the Central Pacific where no permanent hydrophone has ever been deployed. If a sound identical to the bloop were produced in any of these unmonitored regions, it would not be recorded, it would not be detected, it would not be named, analysed, or debated. It would simply occur and vanish, unheard by any human instrument, swallowed by the silence of an ocean that has no obligation to make itself understood. This is not a hypothetical concern. It is a statistical certainty. The probability that every acoustically significant event in the deep ocean has occurred within range of one of the handful of hydrophone arrays currently in operation is essentially zero. There are sounds being produced in the deep ocean right now, at this very moment, that no instrument is recording. Some of these sounds may be routine, variations on themes already catalogued by acoustic researchers. Others may be entirely novel, produced by sources we have not yet encountered. We have no way of knowing the ratio between the familiar and the unfamiliar because we are not listening to most of the ocean. The acoustic landscape we have documented is a sample, and like all samples, it may or may not be representative of the whole. The Argo program, an international array of autonomous profiling floats deployed throughout the world's oceans, represents one of the most ambitious attempts to monitor the ocean on a global scale. As of recent counts, more than 3,900 Argo floats are operating across the world's oceans, drifting at depth and periodically surfacing to transmit data on temperature, salinity, and pressure via satellite. The program has revolutionized our understanding of ocean circulation, heat content, and climate dynamics. But Argo floats do not carry acoustic sensors. They do not record sounds. They measure physical properties of the water column, but are deaf to the acoustic environment through which they drift. A world in which every Argo float carried a hydrophone would give us an acoustic picture of the ocean that is orders of magnitude more complete than what we currently possess. Such a world does not yet exist, and the cost of creating it, while modest compared to many other scientific programs, has not been funded. In the meantime, the ocean continues to produce sounds we cannot identify, support ecosystems we have not discovered, and conceal features we have not mapped. Every year, new species are described from the deep. Every decade, new types of ecosystems are revealed. Every generation of instruments detects phenomena that the previous generation missed. The trajectory of discovery is not one of diminishing returns. It is one of accelerating surprise. The more we look, the more we find. And what we find is consistently stranger, more complex, and more alive than we expected. The bloop is a symbol of this larger truth. It is a reminder that the most alien, most mysterious, most unexplored environment accessible to human beings is not on another planet or in another galaxy. It is beneath our feet, beneath the hulls of our ships, beneath the surface of the water we swim in on summer days without giving it a second thought. The ocean is here, it is now, it is enormous, and it is still, after all these centuries of human civilization, almost entirely unknown. The deep ocean is sometimes described as the last frontier on Earth. This is accurate, but it undersells the point. The deep ocean is not merely the last frontier, it is the largest for freeware. It occupies more volume than all the land habitats on Earth combined. It contains more potential habitats for life than any other environment we know of. And it operates under conditions so extreme, so alien, so unlike the surface world, that the organisms it contains have evolved solutions to the problems of existence that are unlike anything in the rest of biology. Antifreeze proteins that prevent bodily fluids from crystallizing in near-freezing water. Pressure-resistant cell membranes that remain functional at hundreds of atmospheres. Bioluminescent organs that produce light through chemical reactions in the absence of any external energy source. Enzymes that function at temperatures that would denature every protein in a human body. These are not speculative technologies from a science fiction novel. These are real adaptations, present in real organisms living in real places on this planet right now. Sensory systems that detect vibrations and chemical traces across distances that would be impossible in the thin, dry medium of air. Reproductive strategies so alien that they bear no resemblance to anything in the familiar catalogue of surface biology. Male anglerfish that permanently fuse to the bodies of females, organisms that reproduce by budding or fragmentation, creatures that can enter states of near-suspended animation for years or decades when food is scarce, and resume normal activity when conditions improve. The catalogue of deep ocean biological innovations is not merely incomplete. It is, by every reasonable estimate, mostly unwritten, and the majority of these adaptations have not yet been documented because the organisms that carry them have not yet been found. The total number of species in the deep ocean is unknown. Estimates range from hundreds of thousands to several million, depending on the methodology and the definition of deep ocean being used. The number that have been formally described, given a scientific name, and placed in the taxonomic system is a small percentage of even the most conservative estimates. Some researchers believe that the number of undiscovered species in the deep ocean exceeds the total number of species currently known from all environments on Earth. This is a staggering claim, but it is not fringe science. It is a mainstream estimate from researchers who have spent their careers sampling the deep and extrapolating from what they find. Every expedition to the deep ocean discovers new species. Not occasionally, not as a rare bonus, every single time. A research cruise that deploys a net or a trawl or a camera to the abyssal plain will bring back organisms that have never been seen before. This has been true for every decade of deep-sea research, and there is no indication that it is slowing down. This means that the rate of discovery is still far below the rate at which new organisms await discovery. The inventory of deep ocean life is not approaching completion. It is barely underway. This context transforms the bloop from a curiosity into something more profound. It is not simply a mysterious sound. It is a data point from a domain we do not understand, a signal from a place we have barely visited, a fragment of a story we have not yet learned to read. And the question is not whether the bloop was ice, or a whale, or a volcano. The question is why we are so comfortable declaring the matter globe when we have explored so little of the environment in which the sound was produced. The confidence of the explanation is not proportional to the completeness of the knowledge. And in the deep ocean, the knowledge is anything but complete. We have drawn a conclusion on insufficient evidence, not because the conclusion is wrong, but because we lack the means to know whether it is right. And we have accepted that conclusion not because it satisfies the requirements of scientific rigor, but because it is the best answer available. And having an answer, any answer, is more comfortable than sitting with the question. The Census of Marine Life, a decade-long international research program that ran from 2000 to 2010, attempted to systematically assess the diversity, distribution, and abundance of life in the world's oceans. The project involved more than 2,700 scientists from over 80 nations, making it one of the largest coordinated biodiversity research efforts in history. When it concluded, the census had catalogued approximately 250,000 known marine species and identified an estimated 750,000 or more species still awaiting discovery. Among its findings were creatures so strange they seemed designed to challenge every assumption about what was biologically possible. In the abyssal waters near Antarctica, researchers found a species of sea spider with a leg span of more than 25 centimeters, a striking example of polar gigantism. In the deep trenches of the western Pacific, they found amphipods, tiny shrimp-like crustaceans, living at depths exceeding 10,000 meters, surviving on organic material that had settled down from the sunlit layers above over the course of weeks or months. In the mid-Atlantic, they documented communities of deep-sea corals that formed reefs, rivaling the complexity and biodiversity of shallow tropical coral reefs, but at depths where no sunlight had ever penetrated. These deep-water corals were centuries old, some estimated at more than 4,000 years, making them among the oldest living organisms on the planet. The census also revealed patterns that had not been expected. Marine species diversity, long assumed to decline steadily with depth, turned out to be far more complex. Certain depth ranges hosted unexpected concentrations of biodiversity, creating what some researchers described as deep-sea oases. The boundaries between water masses of different temperatures and salinities acted as ecological borders, concentrating life along their margins, in much the same way that the edges of forests and grasslands concentrate terrestrial species. The deep ocean, it turned out, was not a uniform, life-poor desert. It was a mosaic of habitats, each with its own community of organisms, its own food web, and its own set of interactions, and the vast majority of these habitats had never been sampled. The census of marine life, for all its ambition and scope, was able to survey only a small fraction of the total deep ocean. Its findings were not a final inventory. They were a preliminary sketch, a first attempt at understanding the outlines of a picture whose full detail remains invisible. The relevance of this to the Bloop is direct and inescapable. Every unidentified sound in the ocean is a question about the completeness of our acoustic catalogue. Every undiscovered species is a reminder that our biological catalogue is similarly incomplete. Every unmapped feature on the ocean floor is evidence that our geological and topographic catalogues are works in progress. The Bloop arose from an environment whose total contents we do not know, whose total acoustic repertoire we have not recorded, and whose capacity for surprise has been demonstrated over and over again throughout the history of deep-sea science. The ocean also plays a role in the planetary systems that sustain human life that is difficult to overstate. It absorbs approximately 30% of the carbon dioxide produced by human activities, acting as a vast chemical buffer against the full impact of greenhouse gas emissions. Without the ocean's capacity for carbon absorption, atmospheric carbon dioxide concentrations would be substantially higher than they currently are, and the rate of climate change would be correspondingly faster. The ocean also absorbs more than 90% of the excess heat generated by greenhouse gas emissions, storing that thermal energy in its deep waters and distributing it through global circulation patterns that influence weather and climate on every continent. It produces roughly half of the oxygen in the Earth's atmosphere through the photosynthetic activity of phytoplankton in its sunlit upper layers, and it supports fisheries that provide the primary source of animal protein for more than 3 billion people worldwide. Despite all of this, the deep ocean receives less scientific attention and less funding than virtually any environment of comparable importance. The annual budget for deep ocean research across all nations is a fraction of what is spent on a single space mission. The number of active deep-sea research programs at any given time can be counted in the dozens, not the hundreds or thousands, and the political will to change this allocation is at present essentially non-existent. The deep ocean does not have a lobby, it does not have a constituency, it does not have a public relations campaign. It is out of sight and, for most of the world's population, out of mind. And yet it is the largest, most biodiverse, most chemically active, and most acoustically complex environment on the planet we call home. The Bloop challenges us to sit with the question, to resist the urge to close the file, to acknowledge that the deep ocean is a place where our familiar tools of explanation reach their limits, and where the only honest response to a question we cannot answer is to say, clearly and without embarrassment, that we do not know, not yet, perhaps not for a long time, but the not knowing is itself informative. It tells us something about the size of our ignorance, the limits of our technology, and the vast, dark, pressurized, unexplored territory that lies between what we have seen and what remains hidden beneath the surface of the world's largest, oldest, and most patient environment. What does it mean to live on a planet you do not understand? This is not a rhetorical question, it is a practical one. The ocean regulates the climate. It produces a significant portion of the oxygen we breathe through the photosynthesis of phytoplankton in its upper layers. It absorbs enormous quantities of carbon dioxide from the atmosphere, acting as the largest active carbon sink on the planet. It drives weather patterns that determine where rain falls and where drought prevails, where hurricanes form and where they die. It feeds billions of people. It produces compounds that are used in medicine, industry, and biotechnology. It is the medium through which global trade flows, with more than 80% of international commerce moving by sea. And we do not know what is in it. Not fully. Not even close. The Bloop forces a confrontation with this reality. It is easy to dismiss a single unidentified sound as a trivial mystery, a curiosity for podcasts and late-night internet browsing. But the Bloop is not trivial. It is emblematic. It represents the tip of an iceberg of ignorance that extends far deeper than most people realize. For every Bloop that was detected, how many similar sounds were produced in regions where no hydrophones were listening? For every hydrothermal vent that has been discovered, how many remain hidden on the unmapped ocean floor? For every species that has been catalogued, how many are living, reproducing, and dying in the abyssal darkness without ever having been observed by a human being or a human instrument? The numbers, even at the most conservative estimates, are humbling. The philosophical weight of this ignorance is considerable. Human beings have constructed an understanding of the world that is, in many respects, remarkably detailed and accurate. We can predict the motion of planets centuries in advance. We can describe the behavior of subatomic particles with extraordinary precision. We can decode the molecular instructions that govern the development of a living organism from a single cell to a complex body with trillions of specialized cells working in coordination. We can reconstruct the history of the universe from a fraction of a second after its origin to the present day, a span of more than 13 billion years. And yet, we cannot tell you what lives at the bottom of most of the ocean. We cannot tell you what sounds are being produced at depths below 3,000 meters in the vast majority of ocean basins. We cannot tell you whether there are geological processes occurring on the deep seafloor that we have not yet conceived of. The contrast between our mastery of some domains and our ignorance of others is stark, almost paradoxical. We can photograph a galaxy 12 billion light-years away, but we cannot photograph most of the floor of our own ocean. There is a tendency, when confronted with this kind of ignorance, to assume that the unknown is simply more of the known, that the unexplored ocean is basically the same as the explored ocean, just with fewer data points, that the sounds we have not yet heard are variations on the sounds we have already classified, that the species we have not yet discovered are minor variants of the species we already know. This assumption is comforting, but it is not supported by the history of ocean exploration. Every major advance in our ability to explore the deep has yielded surprises, not confirmations. Hydrothermal vents were a surprise. No one predicted that the seafloor would contain volcanic fissures, spewing superheated, mineral-laden water into the freezing abyss, much less that these fissures would support entire ecosystems independent of sunlight. Brine pools were a surprise. The idea that the ocean floor could contain lakes of hypersaline water with distinct surfaces and shorelines was not anticipated by any theoretical model. Chemosynthetic ecosystems were a surprise, overturning the long-held assumption that all life on Earth was ultimately dependent on solar energy. Giant tube worms, thriving without mouths or digestive systems, sustained entirely by symbiotic bacteria that metabolize hydrogen sulfide, were a surprise. The giant squid, alive in its natural habitat, its enormous eye catching the faint glow of a camera's light at a depth of 900 meters, was a surprise. The deep ocean has, at every stage, proven to be stranger, more diverse, and more capable of supporting life than we predicted. This pattern should give us pause when we consider the bloop. The default explanation, ice calving, is the explanation that requires the fewest new assumptions. It is the explanation that fits most comfortably within existing knowledge, and it may well be correct. But the history of deep ocean science tells us that the explanation that fits most comfortably within existing knowledge is not always the right one. Sometimes the right answer is the one that requires us to expand our knowledge, to admit that our categories are incomplete, and to accept that the ocean contains things we have not yet imagined. This is not wishful thinking. It is historical pattern recognition. Every generation of deep-sea researchers has encountered phenomena that the previous generation considered impossible. There is no reason to believe that our generation is the one that has finally seen everything. This is not an argument for believing in sea monsters. It is an argument for epistemic humility, for recognizing that our confidence in any explanation is bounded by the completeness of our data, and that in the deep ocean, our data is profoundly incomplete. For understanding that the phrase solved mystery should be used with caution when the environment in which the mystery occurred remains 95% unexplored. For approaching the unknown not with fear or with fantasy, but with the honest acknowledgement that we do not know, and that not knowing is itself a form of knowledge, perhaps the most important form. The willingness to say we do not know is not a failure of science. It is science at its most honest. The pretense of certainty in the face of insufficient evidence is the failure. There is also a deeper philosophical question embedded in the Bloop story, one that extends beyond marine science into the nature of human understanding itself. We are a species that craves narrative closure. We want beginnings, middles, and endings. We want problems identified and solutions delivered. We want mysteries posed and mysteries solved. The open question, the unresolved tension, the ambiguity that resists resolution, these are states that the human mind finds deeply uncomfortable, and so we reach for closure wherever we can find it, even when the evidence does not fully support it. The Bloop was given an explanation. The explanation was reasonable, and the discomfort of the unknown was relieved. But the relief was premature. The question was not answered, it was merely quieted. And the ocean, vast and patient and indifferent to human comfort, continues to ask it. The ocean does not owe us answers. It does not organize itself for our convenience. It does not produce sounds in frequencies we can easily hear, or place its most extraordinary creatures in locations we can easily reach, or time its most dramatic events for moments when our instruments happen to be recording. The ocean is vast, indifferent, and patient. It has been here far longer than we have. It will be here long after we are gone. And in the meantime, it keeps its own counsel, producing sounds in the darkness, sustaining life in the silence, and occasionally, just occasionally, allowing a fragment of its secrets to reach the surface, carried on a pressure wave that travels 5,000 kilometers through the deep sound channel to arrive at a microphone that was never meant to hear it. The Bloop is that fragment. And the question it asks is not what made the sound. The question it asks is what else is down there that we have not yet heard. There is a responsibility embedded in this question, and it is a responsibility that extends beyond the scientific community to society at large. The deep ocean is not merely a subject of academic curiosity. It is a critical component of the planetary systems that sustain all life on Earth, including human life. Changes in deep ocean circulation patterns can alter global climate on timescales of decades to centuries. The release of ethane trapped in deep-sea hydrate deposits could accelerate warming in ways that current climate models do not fully account for. The acidification of deep waters, driven by the absorption of excess atmospheric carbon dioxide, is already affecting deep-sea ecosystems in ways that are poorly understood. The extraction of deep-sea minerals through seafloor mining, a nascent industry that is rapidly gaining commercial momentum, poses risks to ecosystems that have not been surveyed, much less understood. Every one of these issues is shaped by the same fundamental problem that the Bloop illustrates. We are making decisions about an environment we do not understand. The cultural impact of the Bloop also deserves examination. Since its detection and subsequent popularization, the Bloop has become one of the most widely referenced ocean mysteries in popular media. It has appeared in documentaries, podcasts, online videos, books, and articles. It has been referenced in fiction and used as the inspiration for countless works of speculative writing. It has become a shorthand for the unknown depths of the ocean and the limits of human knowledge. This cultural resonance is not accidental. The Bloop resonates because it touches something fundamental in the human psyche. A deep and ancient awareness that the ocean is a place of mystery, a place where the familiar rules of the surface world do not apply, a place where things exist that are larger, stranger, and more powerful than anything in our everyday experience. The Bloop gives a name and a shape to this awareness. It transforms an abstract feeling into a concrete event, a specific sound, a particular spectrogram, a definite set of coordinates. And in doing so, it makes the ocean's mystery tangible in a way that statistics and surveys cannot. But cultural resonance carries its own risks. The Bloop's fame has in some ways distorted the broader conversation about deep ocean science. It has encouraged a focus on mystery and spectacle at the expense of the quieter, more rigorous work of systematic exploration and documentation. It has fostered an either-or framing, monster versus ice, that reduces a complex scientific question to a binary choice. And it has, paradoxically, allowed the icequake explanation to function as a kind of intellectual sedative, reassuring the public that the mystery has been solved and that there is nothing more to see. The reality is that there is everything more to see. The bloop is one sound among an unknown number of sounds that the ocean produces. It is one mystery among an unknown number of mysteries that the deep ocean harbours, and the attention it has received, while welcome, represents a tiny fraction of the attention that the deep ocean as a whole deserves. What the bloop ultimately teaches us is not about ice or whales or unknown creatures. It teaches us about the limits of certainty in a world of incomplete data. It teaches us about the danger of declaring a question, answered when the evidence, while suggestive, falls short of proof. It teaches us about the vast gap between what we know and what we think we know, a gap that is nowhere wider than in the deep ocean. And it teaches us, if we are willing to listen, that the most honest and most scientifically productive response to a genuine mystery is not to close it prematurely, but to hold it open, to keep asking, to keep listening, and to keep exploring the extraordinary, terrifying, beautiful, and largely unknown world that lies beneath the surface of the sea. The deep ocean has been patient with us. It has waited through the entire span of human civilization for us to develop the tools and the will to begin exploring it in earnest. It has offered glimpses of its contents, a sound here, a creature there, a landscape revealed by the lights of a submersible for the first time in billions of years, and it has accepted, without complaint, our premature declarations of understanding. The ocean does not argue with us. It does not correct our mistakes. It simply waits, in its darkness, in its cold, in its silence, for us to return. And when we do return, with better tools and deeper questions, it will show us something we did not expect. It always does. There is something about the ocean at night, when the surface is dark and the sky is dark, and the only boundary between them is a thin, shifting line of reflected starlight. At those moments, standing on the deck of a ship, or on the edge of a shore, it is possible to feel the true scale of the water. Not to know it intellectually, but to feel it. To sense the depth beneath you, the weight of it, the silence of it, the sheer, incomprehensible volume of a world that exists below the surface, and asks nothing of you, and offers nothing in return except the occasional reminder that it is there. The bloop was one such reminder, a sound from the deep, a rising note in the darkness, a signal from a place so remote that the nearest human beings were orbiting the planet in a space station. It lasted roughly 1 minute. It was heard across 5,000 kilometers of ocean. It was given a name, a file, a spectrogram, and eventually a tentative explanation. And then the ocean fell silent again. Not truly silent, of course. The ocean is never truly silent. It is filled with sounds at every depth and every frequency, an endless, layered composition that no human ear has ever heard in its totality. The songs of whales, whose calls can travel across entire ocean basins and persist for hours. The crackle of snapping shrimp, whose collective noise can be so intense that it creates a wall of sound detectable on sonar. The groan of shifting ice as massive plates flex and fracture under their own weight. The rumble of undersea earthquakes, sending shudders through the water column that travel for thousands of kilometers. The strange rhythmic pinging of unknown sources that appear on hydrophone recordings and vanish without explanation. The ocean is an orchestra playing without a conductor, without an audience, and without a score. It plays for itself, to itself, in the dark. But the bloop, that specific sound, that particular rising note, from that particular point in the southern Pacific, was not heard again. It appeared once, during the summer of 1997, and then it was gone. Whatever process produced it, whether the fracturing of ancient ice, the call of an organism we have not identified, the eruption of a geological feature we have not mapped, or some other process we have not yet conceived, that process either ceased, moved, or changed in a way that rendered it undetectable. The hydrophones continued listening. They recorded other sounds, other anomalies, other fragments of the ocean's endless conversation with itself. But the bloop did not return. It came and went like a word spoken in a vast empty cathedral, a single syllable that carried the weight of all the questions we have ever asked about what lies beneath the waves, echoing for a moment, and then dissolving into the silence from which it emerged. We do not know what made it. We have hypotheses, we have models, we have the reassuring weight of scientific consensus pointing toward ice as the most likely source, and perhaps that is what it was. A chunk of Antarctic ice, ancient and massive, fracturing in the cold water, sending a pulse of acoustic energy racing northward through the deep sound channel until it registered on instruments designed to listen for nuclear submarines. Perhaps that is the entire story. Ice broke, sound travelled, microphones recorded, scientists analysed, mystery solved. Perhaps the bloop is nothing more than a footnote in the history of ocean acoustics, a briefly famous anomaly that was eventually explained by a well-understood physical process. And if that is the case, then the bloop has still served a purpose, because it drew the world's attention, if only for a moment, to the staggering reality of the deep ocean and the enormity of what we do not know about it. Even as a solved puzzle, the bloop is a window into a world that most people never think about. Even as ice, it is a revelation. Because the fact that a simple process like ice fracturing can produce a sound powerful enough to be heard 5,000 kilometers away, in one of the most remote corners of the planet, by instruments listening for nuclear weapons, tells us something important about the scale and power of the forces at work beneath the ocean's surface. If ice alone can speak that loudly, what else is speaking down there that we have not yet heard? But perhaps it is not the entire story. Perhaps the ocean, in its immensity, produced something on that summer day in 1997 that does not fit neatly into our existing categories. Perhaps the sound was produced by a process we have not yet documented, in a region we have not yet explored, under conditions we have not yet observed. Perhaps the bloop is not a closed file, but an open question, one that will remain open until we develop the tools and devote the resources necessary to truly explore the deep ocean. All of it, not just the 5% we have managed to glimpse through the tiny windows of our submersibles and the limited ears of our hydrophones. What we know is this: the ocean is the largest environment on Earth. It is the least explored. It is the most mysterious. It produces sounds we cannot explain, supports life we have not catalogued, and contains landscapes we have not mapped. It is, in every meaningful sense, the unknown world. And the bloop, that 1-minute rising note from the southern Pacific, is the sound of the unknown world reminding us that it exists, that it has a voice, that it speaks in frequencies we are only beginning to learn to hear, and that what it has to say may be more important, more revelatory, and more humbling than anything we have ever imagined. The deep ocean does not care about our theories. It does not care about our instruments. It does not care about the names we give to the sounds we overhear. It simply is. It has been here for longer than we can meaningfully comprehend, forming and reforming through geological ages that dwarf the entire span of human existence. It was here when the first single-celled organisms learned to harvest the energy of sunlight. It was here when the first fish ventured into the abyssal depths. It was here when the first whales returned to the sea and learned to sing in frequencies that travel across hemispheres. It was here when the first human beings looked out at the water from the shore and wondered what lay beneath. And it will be here long after every hydrophone has fallen silent and every spectrogram has faded from every screen. It is the oldest darkness, the deepest silence, the most patient mystery, and somewhere within it, something once rose from the black water and spoke a wingle word that lasted 1 minute and travelled 5,000 kilometres and was heard by machines designed to listen for the end of the world. We called it the bloop, we said it was ice, and then we went back to our lives on the surface, in the sunlight, where the water is warm and the sounds are familiar and the darkness is only a memory of the night before. But the ocean did not go back. The ocean never goes back. It stays, it waits, it listens. And deep in the southern Pacific, in the cold water beneath the empty sky, at the farthest point from any human shore, the silence has settled again over the place where the sound was born. It is a silence that is not empty. It is a silence that is full of pressure, full of cold, full of the weight of 11 kilometers of water pressing down on a world we have never seen, full of life we have not named, full of processes we have not described, full of sounds we have not heard and may never hear unless we find the will to go back, to lower our instruments into the deep, to listen with patience and humility, and to accept whatever answers the ocean chooses to offer. The bloop was a whisper. The ocean has much more to say. And the question that remains, the question that has always remained, is not what the bloop was. It is whether we are willing to keep listening long enough to find out what comes next. Somewhere in the southern Pacific, in the cold and the dark and the crushing pressure of the abyss, the ocean is still speaking. The question is whether anyone is there to hear it. We began this journey with a single sound, a rising note from the summer of 1997. We end it with a question that is far larger than the sound that prompted it. What is the ocean hiding? What is it saying? And will we ever develop the patience, the humility, and the resources to truly listen?